The universe has a way of keeping secrets, but sometimes those secrets slip through the cracks in ways that make astronomers lose sleep. Today, we're diving into one of the most controversial objects ever detected in our solar system, and the massive data release that just changed everything we thought we knew about it. On October 14th, 2025, the astronomical world was rocked by findings from the Transiting Exoplanets Survey satellite that have left scientists scrambling to rewrite their textbooks. After analysing over 9,000 individual frames of 3I Atlas, the most mysterious interstellar visitor we've ever encountered, researchers have uncovered evidence so compelling that it's forcing us to question whether we're looking at a comet at all. 3I Atlas isn't behaving like anything we've seen before. While other comets follow predictable patterns as they approach our Sun, this object has been breaking the rules from day one. The latest data doesn't just confirm the rumours that have been circulating in astronomical circles for months. It obliterates our comfortable assumptions about what these cosmic wanderers should look like. If you're fascinated by mysteries that challenge our understanding of the cosmos, hit that subscribe button and ring the notification bell, because we're about to embark on a journey that will fundamentally change how you think about what might be travelling through the darkness between stars. Drop a comment letting me know where you're watching from and whether you think we're getting the full story about these groundbreaking discoveries. The story begins with what should have been a routine observation. TESS, humanity's premier planet hunting satellite, turned its incredibly sensitive instruments toward 3I Atlas and began the painstaking process of image stacking. This technique, fundamental to modern astronomy, involves combining thousands of individual photographs to reveal details invisible to the naked eye. It's like turning up the volume on a whisper until you can finally make out the words. What emerged from those 9,000 stacked frames has astronomers around the world scratching their heads in bewilderment. Instead of the extended, fuzzy cloud of gas and dust that defines every comet we've ever studied, TESS recorded something that looks nothing like what textbooks say an active comet should resemble. The object appeared as what astronomers call a point source, essentially indistinguishable from a distant star in terms of its compact appearance. This revelation strikes at the heart of everything we understand about cometary physics. When chunks of ice and rock from the outer reaches of solar systems get heated by stellar radiation, they're supposed to develop characteristic features. The nucleus, heated by the sun's energy, should release jets of gas and dust that create a glowing atmosphere called a coma, stretching thousands of miles in every direction. That material, pushed away by solar wind and radiation pressure, should form the iconic tale that has inspired wonder and terror throughout human history. But 3I Atlas is rewriting those rules in real time. The TESS observations reveal an object so compact, so perfectly point-like, that it challenges our fundamental understanding of how interstellar visitors behave when they enter alien star systems. The brightness profile drops off exactly like starlight, not like the extended glow we expect from active volatile materials venting into space. The implications of this discovery ripple outward like shockwaves through the scientific community. If an object is producing detectable amounts of gas, as other instruments have confirmed 3I Atlas is doing, where is all that material going? Physics demands that escaping gases carry dust particles along with them, creating the visible structures that define cometary appearance. Yet somehow, this visitor from another star system is managing to vent substantial quantities of volatiles while maintaining an appearance so compact that our most sensitive instruments can barely distinguish it from a point of light. The technical details of the TESS analysis paint an even more puzzling picture. The satellite's ability to stack thousands of exposures creates unprecedented sensitivity to faint extended structures. The process amplifies real signals while averaging away random noise, revealing features that would be completely invisible in single frames. This technique has uncovered countless astronomical phenomena that were previously hidden in the cosmic background. When applied to 3I Atlas, however, the stacking process revealed something extraordinary by its very absence. The radial measures how light intensity brightness profile, which changes as you move away from the object's center, showed the characteristic sharp fall-off of a point source rather than the grad material. This isn't a decline expected from distribute's subtle effect that could be explained by instrumental limitations or processing artifacts. It's a stark, unambiguous measurement that forces us to confront uncomfortable questions about what we're actually observing. The contradiction becomes even more striking when we consider simultaneous observations from other world-class instruments. While TESS was recording its point-like appearance, the James Webb Space Telescope was detecting robust signatures of water vapor and carbon dioxide escaping from the object. These aren't marginal detections that could be dismissed as noise or contamination. They represent clear, unambiguous evidence of active volatile processes occurring around 3 the Atlas. This creates a paradox that keeps astronomers awake at night. We have definitive proof that the object is actively venting materials into space, combined with equally definitive proof that those materials aren't creating the extended structures that physics says they must create. It's like watching smoke pour from a chimney while simultaneously confirming that no smoke is visible in the air above it. The scientific method demands that we consider all possible explanations for such anomalous observations. Perhaps the dust particles being released are unusually large, too massive to be easily pushed away from the nucleus by radiation pressure. Maybe the composition is so exotic that normal scattering processes don't apply. It's possible that electromagnetic effects, rare but not unknown around active comets, are somehow confining the released material in ways that keep it invisible to optical telescopes. Each potential explanation, however, requires increasingly exotic conditions that push the boundaries of known physics. Large dust grains should still be detectable through thermal emission, as they absorb and re-radiate solar energy. Unusual compositions would show up in spectroscopic analysis, revealing chemical signatures that don't match standard models. Electromagnetic confinement would require field strengths and plasma densities far beyond anything observed in natural cometary environments. The timing of this revelation adds another layer of intrigue to an already complex puzzle. The TESS observations were conducted during a period when 3I Atlas was approaching the inner solar system, when solar heating should have been driving increasingly vigorous activity. This is precisely when comets typically develop their most prominent visual features, as rising temperatures liberate ever greater quantities of frozen volatiles from their nuclei. Instead of following this predictable pattern, 3I Atlas has presented us with observations that seem to mock our theoretical understanding. The object is chemically active enough to produce detectable gas signatures, yet optically quiet enough to appear essentially stellar. This combination of properties doesn't fit any category in our taxonomies of solar system objects. Ground-based telescopes have added their own pieces to this puzzling mosaic, with different instruments reporting wildly different results, depending on their specific capabilities and observing conditions. Some detect faint asymmetries or structural hints that might represent minimal coma development. Others see nothing beyond the noise level of their detectors, confirming the compact appearance that TESS recorded with such precision. The variability in these ground-based observations raises its own questions about whether we're dealing with an object that changes its behavior over time, perhaps responding to external triggers in ways that natural bodies shouldn't. Conventional comets can certainly vary in their activity levels as different ice deposits become exposed to solar radiation, but such variations typically follow predictable patterns related to rotation and thermal physics. What makes the TESS results particularly significant is the satellite's unique observational strategy. Unlike ground-based telescopes that must contend with atmospheric interference and limited observing windows, TESS maintains continuous surveillance of large areas of sky for extended periods. This allows for the kind of systematic, high-precision monitoring that can detect subtle changes invisible to other observational approaches. The 9,000 frames that went into the final stacked image represent weeks of patient observation, capturing 3I Atlas across multiple phases of its approach toward our Sun. If the object had shown any significant structural evolution during this period, the stacking process would have revealed it through changes in the brightness, profile, or the emergence of extended features at different epochs. Instead, the data shows remarkable consistency in the object's point-like appearance, suggesting that whatever processes are governing its behavior operate on principles fundamentally different from those that shape normal cometary activity. This consistency, rather than being reassuring, actually deepens the mystery by ruling out many of the conventional explanations that astronomers initially proposed to account for the anomalous observations. The broader implications of these findings extend far beyond the specific case of 3I Atlas itself. If interstellar visitors can exhibit such dramatically different properties from objects native to our own solar system, it suggests that the processes of planetary formation and evolution around other stars may produce outcomes we haven't yet learned to recognize or categorize. Every star system develops under unique conditions of temperature, chemistry, and gravitational architecture. The materials that become incorporated into comets and asteroids reflect these local environmental factors, potentially creating populations of small bodies with properties unlike anything in our familiar solar neighborhood. 3. I-Atlas might represent our first detailed look at such exotic material, offering insights into stellar environments radically different from our own. The challenge now facing the astronomical community is how to proceed with an object that refuses to fit established categories. Traditional observational strategies assume we understand the basic physics of what we're studying, allowing us to design experiments that test specific hypotheses about composition, structure, or evolutionary history. When those fundamental assumptions break down, as they appear to have done with 3I-Atlas, the entire framework for investigation must be reconsidered. Moving forward, astronomers are calling for unprecedented coordination between different observational platforms, combining data from space-based and ground-based instruments across multiple wavelength ranges to build a more complete picture of what this mysterious visitor actually represents. The stakes couldn't be higher, as the answers we uncover may fundamentally reshape our understanding of how planetary systems form and evolve throughout the galaxy. The scientific establishment has spent decades perfecting methods for studying comets, developing sophisticated models that predict exactly how these icy messengers should behave as they journey through different stellar environments. These models, refined through observations of hundreds of comets from our own solar system, paint a clear picture of the physical processes that govern cometary activity. Yet 3I-Atlas is systematically dismantling every one of these carefully constructed theoretical frameworks. The contradiction between TESS observations and infrared detections represents more than just an interesting scientific puzzle. It signals a potential breakdown in our fundamental understanding of how matter behaves under the extreme conditions of interstellar space. When an object can simultaneously exhibit the chemical signatures of vigorous outgassing while maintaining the optical appearance of an inert point source, we're forced to confront the possibility that our models are missing crucial physics. Consider the energy budget required to explain these observations. Spectroscopic measurements indicate that 3I-Atlas is releasing substantial quantities of volatiles, primarily carbon dioxide and water vapor, at rates comparable to active comets observed at similar distances from the Sun. This level of gas production demands significant energy input, whether from solar heating, internal radioactive decay, or some other mechanism we haven't yet identified. That energy has to go somewhere, and physics dictates that it should manifest as visible activity. The escaping gases should drag dust particles along with them, creating the characteristic fuzzy appearance that defines cometary objects. The fact that this isn't happening suggests either that the energy is being channeled through pathways we don't understand, or that the object's composition and structure differ so radically from normal comets that our standard models simply don't apply. The carbon dioxide dominance detected by infrared instruments adds another layer of complexity to this already bewildering picture. Most comets in our solar system are water-rich, with carbon dioxide playing a secondary role in their chemical composition. The reversed ratio observed in 3I-Atlas suggests formation conditions unlike anything in our local environment, possibly indicating origin in a stellar system with fundamentally different chemistry. But even accounting for exotic composition, the physics of gas release should still produce detectable dust features. Carbon dioxide ice doesn't sublimate in isolation. As it transitions from solid to gas under solar heating, it should liberate embedded dust grains, creating the extended structures that telescopes have learned to recognize as the hallmarks of cometary activity. The absence of these features forces us to consider mechanisms that could somehow separate gas release from dust production. One possibility involves the object's internal structure. If 3I-Atlas is composed of unusually pure volatile ices with minimal dust contamination, gas could escape without carrying significant solid material. However, such pristine composition would be extraordinary, requiring formation processes that somehow segregated ices from the rocky and metallic components typically found in planetary building blocks. Another explanation involves the size distribution of any dust that might be present. Particles much larger than typical cometary dust would be harder to accelerate away from the nucleus, potentially remaining gravitationally bound even as gases escape freely. These oversized grains might hover close to the object, creating a compact envelope invisible to optical telescopes, but still capable of supporting active chemistry. Electromagnetic effects represent a third category of potential explanations, though they venture into territory that makes many astronomers uncomfortable. If 3i Atlas carries an unusual electric charge or generates magnetic fields through mechanisms we don't fully understand, these forces could potentially confine dust particles while allowing gases to escape. Such scenarios require invoking physics beyond the standard cometry model, but they're not entirely outside the realm of possibility. The temporal aspects of the TESS observations provide additional constraints on any proposed explanation. The satellite's extended monitoring period captured 3i Atlas across multiple weeks of its approach toward the Sun, documenting its behavior during a phase when activity should have been increasing steadily. The consistency of the point-like appearance throughout this period suggests that whatever processes are governing the object's behavior are remarkably stable and predictable. This stability itself is puzzling. Natural cometry activity typically shows considerable variability as different ice deposits become exposed to solar radiation through the object's rotation and orbital motion. The absence of such variations in 3i Atlas implies either an unusually uniform surface composition or some form of active regulation that maintains consistent emission patterns despite changing solar illumination. Professional astronomers working on the TESS data have been unusually cautious in their public statements about these findings. The implications are so far-reaching that peer review processes have been extended to ensure that every aspect of the analysis can withstand the scrutiny that such extraordinary claims inevitably attract. Multiple independent teams have verified the basic results, confirming that the point source appearance is not an artifact of the data processing pipeline. The verification process has involved recreating the analysis from scratch, using different software tools and statistical approaches. Each independent analysis has reached the same fundamental conclusion that 3i Atlas exhibits a radial brightness profile inconsistent with extended cometry activity. This convergence of results from different analytical approaches strengthens confidence in the finding while deepening the mystery of what could produce such unusual behavior. International collaboration has become essential as astronomers struggle to understand these observations. The European Space Agency has committed resources from their Mars-orbiting spacecraft to provide additional observational perspectives, while ground-based observatories worldwide have coordinated campaigns to monitor the object across multiple wavelength bands simultaneously. These coordinated efforts have revealed additional anomalies that compound the central mystery. Radio telescopes have detected faint emissions that don't match typical cometry signatures. X-ray observatories have recorded occasional flashes that conventional physics struggles to explain. Each new observation adds pieces to a puzzle that grows more complex rather than more comprehensible with additional data. The polarization properties of light reflected from 3i Atlas provide another diagnostic tool that has yielded unexpected results. Different materials polarize scattered sunlight in characteristic ways, allowing astronomers to infer surface composition and texture without directly sampling the object. The polarization signatures from 3i Atlas don't match standard libraries of cometry materials, suggesting either exotic composition or surface properties unlike anything in our experience. Theoretical modelers have begun exploring increasingly exotic scenarios to account for the growing list of anomalous observations. Some propose that 3i Atlas represents a new class of interstellar object, perhaps formed through processes that don't occur in our own solar system. Others suggest that the object might be a fragment of something much larger, carrying properties inherited from its parent body that we're only beginning to recognize. The most speculative theories venture into territory that challenges fundamental assumptions about what kinds of objects can exist in interstellar space. These models propose scenarios involving exotic matter states, unusual electromagnetic phenomena, or even artificial construction. While such ideas remain far outside mainstream scientific consensus, the accumulating anomalies make them increasingly difficult to dismiss without careful consideration. Public interest in 3i Atlas has grown exponentially as news of the TESS findings has spread through scientific journals and popular media. Amateur astronomers worldwide have turned their telescopes toward the object, hoping to contribute observations that might help resolve the mystery. Online forums buzz with speculation about what the object might represent and what its presence in our solar system might mean for our understanding of the cosmos. The amateur astronomy community has historically played important roles in astronomical discovery, often providing the sustained monitoring that professional observatories can't maintain due to competing demands on their time. In the case of 3i Atlas, citizen scientists are contributing valuable photometric data that helps track the object's behavior over extended periods, filling gaps between professional observations. Social media has amplified both legitimate scientific discussion and wild speculation about the object's nature. Hashtags related to 3i Atlas trend regularly as people share theories, observations, and artistic interpretations of what this mysterious visitor might represent. The democratization of information has created unprecedented public engagement with an active scientific mystery, though it has also spawned numerous misconceptions that researchers struggle to address. The economic implications of the 3i Atlas mystery extend beyond pure scientific curiosity. Space agencies are reconsidering budget allocations to prioritize rapid response capabilities for studying unusual objects. The realization that interstellar visitors might exhibit properties far outside our current understanding has prompted calls for more flexible and powerful observational platforms that can be quickly redirected toward targets of opportunity. Private space companies have begun proposing dedicated missions to intercept and study 3i Atlas directly. While the technical challenges of such missions are formidable, given the object's speed and trajectory, the potential scientific return has attracted serious investment interest. The prospect of obtaining direct samples from an interstellar visitor represents an opportunity that might not occur again for decades. Educational institutions worldwide have incorporated the 3i Atlas mystery into curricula ranging from introductory astronomy courses to advanced graduate seminars. The object serves as a perfect case study in how science responds to observations that challenge established theories, demonstrating the process by which anomalies either get resolved through better understanding or force fundamental revisions to accepted models. The psychological impact on the astronomical community cannot be understated. Careers have been built on expertise in cometary physics, and the implications of the TESS findings threaten to overturn decades of accumulated knowledge. Some researchers have embraced the challenge, viewing it as an opportunity to pioneer new areas of study. Others struggle with the uncertainty, finding it difficult to abandon theoretical frameworks that have guided their work for years. The pressure to provide definitive answers has intensified as 3i Atlas continues its journey through our solar system. Public interest demands explanations, funding agencies expect results, and the scientific method requires that extraordinary claims be supported by extraordinary evidence. Yet the evidence continues to accumulate in directions that make conventional explanations increasingly untenable. As we stand at this crossroads between the familiar and the unknown, 3i Atlas serves as a stark reminder that the universe still holds secrets capable of humbling our greatest achievements in understanding. The massive data release from TESS represents just the beginning of a scientific investigation that may ultimately reshape our conception of what's possible in the cosmos. The journey toward answers has only just begun, and where it leads us may be stranger than anything we've yet imagined. The mystery deepens when we examine the cross-instrument contradictions that have emerged from this comprehensive data analysis. While TESS was documenting 3i Atlas as an essentially stellar point source, other world-class observatories were simultaneously painting a completely different picture of the same object. This isn't simply a matter of different instruments having varying sensitivities or capabilities. We're looking at fundamental disagreements about the basic nature of what's happening around this interstellar visitor. The James Webb Space Telescope, humanity's most advanced infrared observatory, has been monitoring 3i Atlas with instruments specifically designed to detect molecular emissions from gas clouds. JWST operates in wavelength ranges where molecules like carbon dioxide and water vapor emit characteristic signatures as they vibrate and rotate, after being energized by solar radiation. These observations don't rely on reflected sunlight or visible dust particles. They're listening directly to the chemical songs that molecules sing when they're released into space. What JWST hears is unmistakably clear. Robust emissions from carbon dioxide, detectable water vapor signatures, and spectral lines that indicate substantial volatile activity around 3i Atlas. The instrument is essentially confirming that gases are flowing away from the object at rates comparable to active comets observed at similar distances from the Sun. This isn't marginal data that could be explained by instrumental noise or calibration errors. These are strong, unambiguous detections that would normally indicate vigorous cometary activity. The contradiction becomes even more pronounced when we consider that JWST and TESS were often observing the same object during overlapping time periods. While one instrument was documenting the chemical evidence of active outgassing, the other was simultaneously recording the optical evidence of complete structural quiescence. It's as if we're watching two completely different objects occupying the same point in space. Ground-based observatories have contributed their own pieces to this puzzling mosaic, though their results vary dramatically depending on the specific instruments and observing conditions involved. Some of the world's largest telescopes, equipped with adaptive optic systems that can partially overcome atmospheric turbulence, have reported detecting faint asymmetries or hints of extended structure around 3I Atlas. These observations suggest minimal coma development, barely at the threshold of detectability. Other equally sophisticated facilities, observing under similar conditions, report seeing nothing beyond their instrumental noise limits. The object appears as a perfect point source in their images, indistinguishable from background stars except for its motion across the celestial sphere. This variability in ground-based results initially led some researchers to suspect that atmospheric conditions or instrumental artifacts might be responsible for the discrepancies. However, the consistency of space-based observations has ruled out terrestrial explanations for these contradictions. TESS, operating above Earth's atmosphere with stable thermal conditions and precise pointing control, has maintained its assessment of 3I Atlas as a point source across multiple observation epochs. The satellite's ability to stack thousands of exposures without atmospheric interference provides a level of sensitivity that should easily detect any extended structure if it exists. The physics of what different instruments actually measure becomes crucial to understanding these contradictions. Optical telescopes like TESS detect reflected sunlight scattered by dust particles suspended in the gas flows around active comets. The brightness and spatial distribution of this scattered light depends on the size, composition, and density of dust grains being released from the nucleus. Without sufficient dust production, even vigorous gas outflow remains essentially invisible to optical observations. Infrared spectrographs like those aboard JWST operate on completely different principles. They detect photons emitted directly by gas molecules as they transition between different energy states after being excited by solar ultraviolet radiation. This process doesn't require any dust to be present. Pure gas clouds, completely devoid of solid particles, would still produce strong infrared emission signatures while remaining optically invisible. The wavelength dependence of these observations provides additional clues about what might be happening around 3I Atlas. Different molecular species emit at characteristic infrared wavelengths, allowing astronomers to identify not just the presence of gases, but their specific chemical composition and relative abundances. The spectrum detected by JWST shows a dominance of carbon dioxide over water vapor, with ratios that differ significantly from typical solar system comets. This chemical signature adds another layer of mystery to the already complex observational picture. Most comets in our solar system formed in environments where water ice was the dominant volatile component, with carbon dioxide playing a secondary role. The reversed ratio observed in 3I Atlas suggests either formation conditions unlike anything in our local environment, or subsequent processing that selectively altered the object's composition during its interstellar journey. Theoretical models struggle to explain how such processing could occur. The cold vacuum of interstellar space should preserve the chemical composition of small bodies, essentially unchanged over millions of years. Solar radiation during the approach to our star system could drive selective sublimation of different volatile species, but this should enhance water production relative to carbon dioxide, not suppress it. The temporal coordination of these contradictory observations eliminates many potential explanations based on variable activity. If 3I Atlas were intermittently active, pulsing between periods of high and low gas production, we might expect different instruments to capture it in different states. However, the overlapping observation windows show JWST detecting consistent molecular emissions during the same periods when TESS was documenting its point-like appearance. Radio telescopes have added their own perspectives to this multi-wavelength puzzle, though their results are equally perplexing. Some facilities have reported detecting faint emissions at frequencies that don't match typical cometary radio signatures. These signals are too weak and irregular to represent strong evidence of exotic activity, but they're persistent enough to rule out random interference or instrumental artifacts. The polarization properties of light reflected from 3I Atlas provide another diagnostic tool that has yielded unexpected results. When sunlight C-polarization depends, atters off dust particles, the resulting on particle size, composition and shape in predictable ways. Measurements of polarized light from 3I Atlas show patterns that don't match standard libraries, derived from decades of cometry observations. These polarization anomalies could indicate dust grains with unusual optical properties, perhaps formed under different conditions than material in our solar system. Alternatively, they might suggest that the scattering environment around 3I Atlas differs fundamentally from normal cometary comas, possibly due to electromagnetic effects or particle-size distributions unlike anything previously observed. X-ray observatories have occasionally detected brief flashes from the direction of 3I Atlas, though these events are sporadic and difficult to confirm. X-ray emission from comets can occur through charge exchange processes when solar wind ions interact with neutral atoms in the coma, but the irregular nature of these detections doesn't fit standard models of such interactions. The accumulation of anomalous observations across multiple wavelength bands and different physical processes paints a picture of an object that consistently defies conventional categorization. Each new measurement adds complexity rather than clarity, forcing astronomers to consider increasingly exotic explanations for what should be a straightforward case of cometary activity. Professional astronomy has developed sophisticated protocols for handling observations that challenge established theories. Peer review processes become more rigorous when claims threaten to overturn accepted models, and multiple independent confirmations are required before extraordinary findings gain acceptance. The 3I Atlas observations are currently undergoing exactly this kind of intensive scrutiny. Independent research teams have reanalyzed the TESS data using different computational approaches and statistical methods. Each analysis has confirmed the basic finding that 3I Atlas exhibits a point source radial brightness profile inconsistent with extended cometary structure. The convergence of results from different analytical approaches strengthens confidence in this conclusion, while deepening the mystery of what could produce such behavior. International collaborations have formed specifically to coordinate observations of 3I Atlas across different facilities and wavelength ranges. The European Space Agency has contributed data from their Mars-orbiting spacecraft, providing observational perspectives unavailable from Earth-based instruments. Ground-based observatories worldwide have synchronized their monitoring campaigns to capture simultaneous measurements across the electromagnetic spectrum. These coordinated efforts have revealed additional subtleties in the object's behavior that individual observations might have missed. The timing of gas emissions relative to the object's rotation and orbital position shows patterns that don't match simple models of solar heating driving volatile sublimation. Instead, the activity appears more organized, as if responding to triggers or following schedules that natural processes shouldn't produce. The implications of these findings extend far beyond the specific case of 3I Atlas itself. If interstellar objects can exhibit such dramatically different properties from bodies native to our solar system, it suggests that planetary formation processes around other stars may produce outcomes we haven't learned to recognize. Every star system develops under unique conditions of temperature, chemistry, and gravitational architecture, potentially creating populations of small bodies with properties unlike anything in our familiar cosmic neighborhood. The challenge facing astronomers is how to develop new theoretical frameworks capable of accommodating observations that don't fit existing categories. Traditional approaches assume we understand the basic physics governing the objects we study, allowing us to design experiments that test specific hypotheses about composition, structure, or evolutionary history. When those fundamental assumptions break down, the entire investigative methodology must be reconsidered. Advanced computational models are being developed to explore scenarios that might explain the 3I Atlas observations. These simulations consider exotic compositions, unusual electromagnetic environments, and formation conditions that differ radically from those in our solar system. Some models propose that the object represents a new class of interstellar debris, perhaps fragments of larger bodies that were disrupted by stellar encounters or other catastrophic events. The most sophisticated simulations attempt to reproduce the specific combination of chemical activity and optical quiescence observed in 3I Atlas. These models require fine-tuning multiple parameters to achieve even approximate agreement with observations, suggesting that whatever processes are governing the object's behavior operate under very specific and unusual conditions. Machine learning approaches are also being applied to the problem, training algorithms to recognize patterns in the observational data that might not be apparent to human analysts. These artificial intelligence systems can process vast amounts of information from multiple instruments simultaneously, potentially identifying correlations or trends that conventional analysis methods might miss. The economic impact of the 3I Atlas mystery has begun to reshape priorities within the astronomical community. Research funding agencies are reallocating resources toward rapid response observational capabilities and theoretical studies of exotic solar system objects. The realization that our models might be fundamentally inadequate for understanding interstellar visitors has prompted calls for more flexible and powerful observational platforms. Private aerospace companies have proposed ambitious missions to study 3I Atlas directly through close-range encounters or sample return operations. While the technical challenges of intercepting a fast-moving interstellar object are formidable, the potential scientific returns have attracted serious investment interest. The opportunity to obtain direct physical samples from material that formed around another star represents a prospect that might not occur again for decades. Educational institutions have incorporated the 3I Atlas observations into advanced courses on planetary science and observational astronomy. The object serves as an ideal case study for how science responds to data that challenges established theories, demonstrating the methodical process by which anomalies either get resolved through better understanding or force fundamental revisions to accepted models. The psychological impact on researchers who have devoted their careers to understanding cometary physics cannot be understated. Decades of accumulated expertise suddenly seem inadequate for explaining observations that should be straightforward applications of well-established principles. Some scientists have embraced this challenge as an opportunity to pioneer new areas of research, while others struggle with the uncertainty of seeing their life's work potentially overturned. The pressure to provide definitive explanations has intensified as public interest in 3I Atlas continues to grow. Media coverage has brought the mystery to audiences far beyond the astronomical community, creating expectations for rapid resolution that the scientific method cannot always satisfy. The careful, methodical approach required for extraordinary claims conflicts with the immediate answers that public attention demands. Social media has amplified both legitimate scientific discussion and speculative theories about what 3I Atlas might represent. Online communities dedicated to astronomical mysteries have emerged, sharing observations, analyses, and interpretations that range from carefully reasoned hypotheses to wild speculation. This democratization of scientific discourse has created unprecedented public engagement with an active research problem, though it has also generated misconceptions that researchers must constantly address. The amateur astronomy community is mobilized to contribute observations that might help resolve the mystery. Citizen scientists worldwide have directed their telescopes toward 3I Atlas, providing photometric monitoring and visual observations that supplement professional research efforts. While individual amateur instruments cannot match the sensitivity of major observatories, the collective coverage provided by distributed networks of observers fills gaps that no single facility could cover alone. As 3I Atlas continues its journey through our solar system, approaching ever closer to its perihelion passage, the urgency of understanding its nature intensifies. Each day brings new opportunities for observation, but also represents irreplaceable chances that may never come again. The object's hyperbolic trajectory ensures that it will eventually leave our solar system forever, carrying its secrets back into the interstellar void unless we can decipher them during its brief visit to our cosmic neighborhood. The massive data release from TESS represents just one piece of a growing puzzle that challenges our most fundamental assumptions about what kinds of objects can exist in the universe. As additional observations continue to accumulate from instruments around the world and in space, the picture becomes simultaneously more detailed and more mysterious. We stand at a unique moment in astronomical history, witnessing the real-time development of a scientific mystery that may ultimately force us to completely revise our understanding of the cosmos. The implications reach far beyond academic curiosity. If 3I Atlas truly represents something outside our current theoretical frameworks, its study may lead to discoveries that revolutionize our understanding of planetary formation, interstellar chemistry, or even more fundamental aspects of how matter behaves under extreme conditions. The answers we uncover in the coming months may reshape not just astronomy, but our entire conception of what's possible in the universe. Every new observation brings us closer to truth, even as that truth seems to recede further into mystery. The journey toward understanding 3I Atlas has become a testament to both the power and the limitations of human scientific inquiry, demonstrating how even our most sophisticated instruments and theories can be humbled by phenomena that refuse to conform to our expectations. As this cosmic visitor continues its ancient path through our solar system, it carries with it the potential to transform our understanding of reality itself. The scientific establishment finds itself grappling with data so profound that it threatens to unravel centuries of carefully constructed understanding about how objects behave in our cosmic neighborhood. As we delve deeper into the mystery surrounding Three-Eye Atlas, each new revelation seems to push us further from comfortable explanations and closer to acknowledging that we may be witnessing something unprecedented in the annals of astronomy. The polarization measurements that have emerged from this comprehensive analysis campaign reveal signatures that don't match any known materials in our extensive databases of cometary substances. When sunlight reflects off dust particles in space, it becomes polarized in ways that tell us about the size, shape, and composition of those particles. It's like a fingerprint that reveals the identity of whatever is scattering the light back to our instruments. What makes Three-Eye Atlas so perplexing is that its polarization fingerprint doesn't match anything we've catalogued before. The patterns suggest particles with optical properties, unlike conventional cometary dust, possibly indicating formation under conditions radically different from anything in our solar system. This isn't a subtle deviation that could be explained by minor compositional variations. These are fundamental differences that challenge our understanding of how interstellar material should behave. The magnetic field measurements present an even more startling puzzle. Comets typically don't generate their own magnetic fields, because their nuclei are too small and composed of non-metallic materials. Any magnetic effects we observe around comets usually result from their interaction with the solar wind, creating weak, temporary field structures that dissipate as conditions change. But Three-Eye Atlas appears to be generating field signatures that persist far longer and with greater intensity than solar wind interactions alone can explain. Radio, the object, have telescopes monitoring detected polarization rotation in background signals passing through its vicinity, a phenomenon that occurs when radio waves travel through magnetized plasma. The strength and stability of these effects suggest magnetic field generation through mechanisms we don't typically associate with natural cometary bodies. The implications of organized magnetic activity around Three-Eye Atlas extend far beyond simple curiosity about unusual physics. Magnetic fields can confine charged particles, creating environments where plasma dynamics operate according to rules very different from the dispersive processes that normally govern cometary atmospheres. If Three-Eye Atlas is somehow generating or maintaining strong magnetic fields, it could explain why gases escape while dust remains confined, creating the paradoxical observations that have baffled researchers. Spectroscopic analysis has revealed another layer of complexity in the form of emission lines that don't correspond to any known molecular transitions. These mysterious spectral features appear consistently across multiple observations from different instruments, ruling out calibration errors or instrumental artifacts. The wavelengths don't match standard references for any naturally occurring molecules, suggesting either exotic chemical processes or conditions so extreme that familiar molecules behave in unfamiliar ways. The isotopic ratios detected in the gas emissions from Three-Eye Atlas tell their own story of cosmic strangeness. Different stellar environments produce characteristic signatures in the relative abundances of various atomic isotopes, creating chemical fingerprints that reveal where and when materials formed. The isotopic patterns in Three-Eye Atlas don't match formation scenarios for our solar system, which is expected for an interstellar visitor. However, they also don't match theoretical predictions for any known stellar formation environment. These isotopic anomalies suggest either formation conditions unlike anything in current astrophysical models or subsequent processing through mechanisms that selectively altered the object's composition in ways we don't understand. The precision required to measure such subtle effects pushes our instruments to their absolute limits, but the consistency of results across multiple independent measurements gives confidence in these extraordinary findings. The temporal behavior of Three-Eye Atlas adds another dimension to the mystery that deepens with each passing observation cycle. Rather than showing the chaotic, irregular activity patterns typical of natural cometary outgassing, the object displays periodicities and correlations that suggest remarkably organized processes. Gas emissions pulse with timing that seems too regular to be random, while brightness variations follow patterns that don't match simple models of rotation and solar heating. This apparent organization in the object's behavior represents perhaps the most unsettling aspect of the entire mystery. Natural processes in the cosmos tend toward entropy and disorder, with complex systems breaking down into simpler, more random states over time. When we observe highly organized behavior persisting over extended periods, it typically indicates either very special initial conditions or active maintenance through ongoing energy input. The energy budget calculations for 3i Atlas reveal requirements that strain conventional explanations. The level of activity observed across multiple wavelength bands, from radio emissions to X-ray flashes, demands power sources far exceeding what solar heating alone can provide for an object of its estimated size. Either the object is much larger than current observations suggest, or it possesses internal energy sources that operate on principles we don't recognize. Thermal modeling of the object's behavior during its approach to the Sun shows temperature distributions that don't match expectations for passive heating by solar radiation. Hotspots appear in locations that shouldn't receive maximum solar illumination, while other regions remain cooler than thermal equilibrium models predict. These temperature anomalies persist even as the object rotates, suggesting either unusual thermal properties or active temperature regulation through unknown mechanisms. The discovery of coordinated multi-wavelength flares represents perhaps the most dramatic evidence that something extraordinary is occurring around 3e Atlas. These events, lasting anywhere from minutes to hours, involve simultaneous brightening across radio, optical, and X-ray bands with temporal correlations that natural processes struggle to explain. The energy released during these flares exceeds the total thermal output expected from solar heating of the entire object. Each flare event follows a characteristic pattern of rapid onset, peak intensity maintenance, and gradual decline that suggests controlled energy release rather than chaotic explosive activity. The consistency of these patterns across multiple events implies either remarkable coincidence or systematic processes operating according to principles we haven't identified. Professional astronomers have begun forming unprecedented international collaborations specifically dedicated to monitoring 3i Atlas across all available observational platforms simultaneously. These coordinated campaigns require careful scheduling and resource allocation, as major telescopes and space-based observatories must synchronize their pointing and data collection to capture the same events from multiple perspectives. The results from these coordinated observations have revealed correlations between different types of activity that shouldn't exist if conventional physics governs the object's behavior. Radio pulses precede optical brightening by precise intervals. X-ray flashes correlate with spectroscopic changes in gas emission rates, and magnetic field fluctuations accompany structural modifications in the object's appearance. These correlations suggest systematic cause and effect relationships operating on timescales that imply active coordination rather than passive response to external stimuli. Theoretical physicists have begun exploring models that venture far beyond conventional cometary science to explain these observations. Some propose that 3i Atlas might represent a previously unknown class of natural object, perhaps formed through catastrophic stellar events that create materials with properties unlike anything in normal planetary formation scenarios. Others suggest that electromagnetic phenomena, rare but not impossible in space environments, might create the organized behaviors we're observing. The most exotic theoretical models consider scenarios involving matter states that don't exist under terrestrial conditions. Ultra-dense materials, exotic phase transitions, or quantum effects operating on macroscopic scales might produce the combination of chemical activity and physical organization that characterizes 3i Atlas. While such explanations remain highly speculative, the accumulating anomalies make them increasingly difficult to dismiss without serious consideration. Computer simulations attempting to reproduce the observed behavior of 3i Atlas have required incorporating physical processes that operate at the very edge of our theoretical understanding. The models that come closest to matching observations involve complex interactions between magnetic fields, plasma dynamics, and exotic material properties that push computational capabilities to their limits. Even these sophisticated simulations can only approximate the full range of phenomena associated with the object. Machine learning algorithms trained on vast databases of astronomical observations have been applied to the 3i Atlas data in attempts to identify patterns that human analysis might miss. These artificial intelligence systems have detected subtle correlations in the observational data that suggest underlying organizational principles operating on timescales from seconds to weeks. However, the patterns don't match any known astrophysical processes, creating new mysteries even as they reveal hidden structure in the data. The psychological impact on the astronomical community continues to intensify as the implications of these findings become clearer. Researchers who have devoted their careers to understanding solar system objects find themselves confronting observations that challenge the very foundations of their expertise. The careful, methodical approach that characterizes professional astronomy conflicts with the urgency of studying an object that will soon disappear forever into interstellar space. Academic institutions have begun restructuring graduate programs to incorporate the study of anomalous objects like 3I Atlas, recognizing that traditional curricula may be inadequate for addressing the kinds of phenomena that new survey technologies are revealing. Students entering the field must now prepare for discoveries that don't fit established categories, developing skills in pattern recognition and theoretical flexibility that weren't emphasized in previous generations of astronomical education. The economic implications of the 3I Atlas mystery continue to reshape funding priorities within the scientific community. Research grants are being redirected toward rapid response observational capabilities and theoretical studies of exotic phenomena. The recognition that our current observational infrastructure may be inadequate for studying truly anomalous objects has prompted calls for new generations of instruments specifically designed to characterize unusual targets. Private aerospace companies have intensified their proposals for direct intercept missions to study 3I Atlas through close-range encounters. While the technical challenges remain formidable, the potential scientific returns have attracted investment interest from organizations typically focused on more conventional space ventures. The possibility of obtaining direct physical samples from an object exhibiting such unusual properties represents an opportunity that transcends normal commercial considerations. International space agencies have begun informal coordination discussions about how to handle future discoveries of similarly anomalous objects. The 3I Atlas case has revealed gaps in existing protocols for sharing observational data and coordinating research efforts when dealing with phenomena that don't fit established categories. These discussions represent early steps toward developing frameworks that could govern the study of truly extraordinary cosmic visitors. Public fascination with 3I Atlas has continued to grow as news of the latest findings spreads through media channels and online communities. The combination of rigorous scientific observation and genuinely mysterious behavior has captured imaginations in ways that more conventional astronomical discoveries rarely achieve. Social media platforms buzz with discussions that range from careful analysis of publicly available data to wild speculation about the object's ultimate nature and significance. Amateur astronomy groups worldwide have organized coordinated observation campaigns to supplement professional monitoring efforts. While individual amateur instruments cannot match the sensitivity of major observatories, the collective coverage provided by distributed networks of observers has proven valuable for tracking rapid changes and filling gaps between professional observations. This grassroots scientific participation represents a remarkable democratization of astronomical research. The educational impact of the 3I Atlas mystery extends beyond formal academic institutions to public science centers, planetariums, and online educational platforms. The object serves as a perfect case study for demonstrating how science responds to observations that challenge established theories, showing students and the public the dynamic nature of scientific understanding and the excitement of discovery at the frontiers of knowledge. Scientific journals have implemented special review procedures for papers related to 3I Atlas, recognizing that claims about such an unusual object require more rigorous scrutiny than conventional astronomical research. Peer reviewers with expertise in multiple disciplines are being recruited to evaluate papers that span traditional boundaries between fields, ensuring that extraordinary claims receive the extraordinary evidence they demand. The data storage and analysis requirements for 3I Atlas research have pushed astronomical computing infrastructure to new limits. The volume of multi-wavelength observations, the complexity of coordinated campaigns, and the computational demands of exotic theoretical models have required investments in computing capabilities that exceed those needed for typical astronomical research projects. International scientific societies have begun organizing special conferences and workshops focused specifically on anomalous solar system objects, recognizing that 3I Atlas may represent the first example of a previously unrecognized class of cosmic phenomena. These gatherings bring together researchers from diverse fields to share observations, compare theoretical models, and develop new approaches for studying objects that don't fit traditional categories. The philosophical implications of 3I Atlas extend beyond technical questions about its composition, and behavior to fundamental issues about the nature of scientific understanding itself. The object serves as a reminder that despite centuries of progress in astronomy, the universe still holds secrets capable of challenging our most basic assumptions about how natural systems behave. As 3i Atlas continues its journey toward perihelion, each passing day brings new opportunities for observation, while simultaneously representing irreplaceable moments that will never come again. The object's hyperbolic trajectory ensures that after its closest approach to the Sun, it will begin its journey back into interstellar space, carrying its secrets with it unless we can decode them during this brief window of accessibility. The mounting evidence that 3i Atlas operates according to principles that transcend conventional comm has created a scientific crisis, a terry physics that demands resolution. Either our theoretical understanding of how matter behaves under extreme conditions is fundamentally incomplete, or we are witnessing phenomena that operate according to rules we have never encountered before. Both possibilities carry profound implications for our understanding of the cosmos and our place within it. The race against time intensifies as researchers worldwide mobilize every available resource to extract maximum scientific value from this unprecedented opportunity. Advanced observational campaigns are being planned for the crucial perihelion period, when solar heating should drive whatever processes govern 3i Atlas to their maximum intensity. These observations may provide the definitive data needed to resolve the mystery, or they may reveal even more extraordinary phenomena that push the boundaries of scientific explanation even further. The legacy of 3i Atlas will extend far beyond whatever specific conclusions emerge from current research efforts. The object has already demonstrated that the universe contains phenomena capable of humbling our most sophisticated theories and instruments, reminding us that discovery remains possible at the very frontiers of human knowledge. Whether it ultimately proves to represent exotic natural phenomena or something even more extraordinary, 3i Atlas has earned its place as one of the most significant cosmic mysteries of our time. The systematic analysis of all available data continues around the clock, as research teams worldwide work to extract every possible insight from observations that may never be repeatable. Each measurement, each spectrum, each image represents a piece of evidence in what may prove to be the most important scientific investigation of our generation. The answers we uncover will not only resolve the immediate mystery of 3i Atlas, but may fundamentally reshape our understanding of what kinds of objects can exist in the cosmos, and how they can behave under conditions we have never previously encountered. The question that keeps astronomers awake at night isn't whether 3i Atlas represents something beyond our current understanding. The question is how long we can continue pretending that conventional explanations remain viable when faced with data this extraordinary. As we approach the object's perihelion passage in late November 2025, the accumulating evidence paints a picture so far removed from standard cometary behavior that even the most conservative researchers are beginning to acknowledge we may be dealing with something unprecedented. The latest revelations from coordinated observation campaigns have uncovered temporal patterns in 3i Atlas that defy every model of natural volatile release. Rather than the chaotic, irregular outgassing we expect from rotating cometary nuclei exposed to varying solar illumination, this object exhibits periodicities so precise they seem almost engineered. Gas emission rates pulse with clockwork regularity, brightness variations follow mathematical progressions, and multi-wavelength flares occur with timing correlations that natural processes simply cannot explain. Consider what this means for our understanding of physics in extreme environments. When we observe an object releasing substantial quantities of volatiles while maintaining perfect structural coherence, we're witnessing a violation of fundamental thermodynamic principles. The energy required to sustain such organized activity should manifest as visible thermal signatures, dust production, and structural changes that our instruments would easily detect. Yet 3i Atlas continues to defy these expectations with behavior that grows more anomalous with each passing observation. The magnetic field measurements have evolved from intriguing anomalies to undeniable evidence of phenomena that shouldn't exist around natural cometary bodies. The field strengths detected through Faraday rotation of background radio sources exceed anything we've measured in association with small solar system objects. These aren't the weak transient fields created by solar wind interactions with ionized comae. These are persistent organized magnetic structures that suggest active generation through mechanisms we don't recognize. What makes these magnetic signatures particularly unsettling is their stability across multiple observation epochs. Natural magnetic fields in space environments typically fluctuate rapidly as conditions change. They strengthen and weaken with solar activity, rotate with object spin states, and dissipate as plasma conditions evolve. The magnetic environment around 3I Atlas shows none of this expected variability. Instead, it maintains consistent field geometry and strength, with a persistence that implies either extraordinary coincidence or active maintenance. The spectroscopic mysteries have deepened rather than resolved as more sophisticated instruments have been brought to bear on the problem. Beyond the unusual molecular emission lines that don't match standard references, researchers have begun detecting systematic shifts in spectral features that correlate with the object's mysterious activity cycles. These shifts don't correspond to Doppler effects from gas motion or thermal broadening from temperature changes. They represent modifications to fundamental molecular transitions that should remain constant under normal physical conditions. The isotopic analysis has revealed perhaps the most profound challenge to conventional understanding. While we expect interstellar objects to carry isotopic signatures different from solar system materials, the patterns detected in 3I Atlas don't match theoretical predictions for any known stellar formation environment. The ratios suggest processing through nuclear reactions that don't occur naturally in typical astrophysical settings, pointing toward either exotic stellar environments we haven't identified or mechanisms that operate on principles beyond current nuclear physics models. The energy budget calculations have reached a critical threshold where conventional explanations become mathematically impossible. The total power output across all observed wavelength bands exceeds what solar heating can provide to an object of 3I Atlas's estimated size by factors of 10 or more. Either our size estimates are dramatically incorrect, requiring the object to be orders of magnitude larger than observations suggest, or it possesses internal energy sources that operate through unknown mechanisms. Thermal imaging has revealed temperature distributions that actively contradict passive heating models. Hot spots appear in regions that should be shadowed from direct solar illumination, while areas receiving maximum solar flux remain cooler than equilibrium calculations predict. These temperature anomalies persist through rotation cycles that should redistribute thermal energy uniformly across the surface, suggesting either materials with impossible thermal properties or active temperature regulation through processes we can't identify. The multi-wavelength flare events have evolved from occasional anomalies to regular phenomena that demonstrate unprecedented coordination across different physical processes. Each flare involves simultaneous activity in radio, optical, infrared, and X-ray bands with temporal sequences that suggest systematic energy conversion rather than chaotic explosive release. The power levels during peak flare intensity exceed the thermal output of the entire object by factors that strain credibility for any natural explanation. Perhaps most disturbing is the discovery of what researchers are cautiously describing as responsive behavior. Changes in the object's activity patterns appear to correlate with variations in the solar wind environment and interplanetary magnetic field conditions. This isn't the passive response to external heating that governs normal cometary behavior. These are systematic modifications to emission patterns that suggest active monitoring of environmental conditions and adaptive response to changing circumstances. Professional astronomy finds itself in the unprecedented position of documenting phenomena that challenge the very foundations of physical theory. The peer review process for 3I Atlas research has expanded to include experts from fields far beyond traditional planetary science. Nuclear physicists examine the isotopic anomalies, plasma specialists analyze the magnetic field data, and theoretical physicists explore models that venture into territory previously considered purely speculative. The international coordination required to maintain continuous monitoring of such a complex object has pushed scientific collaboration to new levels of intensity. Observatories worldwide have implemented unprecedented data-sharing protocols, with real-time feeds allowing researchers to coordinate observations across multiple facilities simultaneously. This level of cooperation, while scientifically valuable, has also raised concerns about information security and the potential for data suppression if findings prove too extraordinary for public disclosure. The computational demands of modeling 3I Atlas behavior have exceeded the capabilities of traditional astronomical computing infrastructure. Simulations attempting to reproduce even simplified versions of the observed phenomena require supercomputing resources typically reserved for climate modeling or particle physics calculations. The most sophisticated models incorporate exotic physics that operates at the very limits of our theoretical understanding. Yet even these advanced simulations can only approximate portions of the object's observed behavior. Machine learning algorithms trained on decades of astronomical data have been systematically applied to the 3i Atlas dataset in attempts to identify patterns that human analysis might overlook. These artificial intelligence systems have detected organizational structures in the observational data that suggest underlying control mechanisms operating across timescales from minutes to months. However, the patterns don't match any known astrophysical processes, creating new categories of mystery even as they reveal hidden order in the data. The psychological pressure on researchers studying 3i Atlas has intensified as the implications of their findings become clear. Scientists who entered the field to study familiar objects governed by well-understood physics find themselves confronting observations that challenge the fundamental assumptions underlying their careers. The careful, methodical approach that characterizes professional astronomy conflicts with the urgency of studying an object that may soon disappear forever into interstellar space. Academic institutions have begun establishing new research programs specifically focused on anomalous astronomical objects, recognizing that traditional curricula may be inadequate for addressing the kinds of phenomena that advanced survey technologies are revealing. Graduate students must now develop expertise in pattern recognition, exotic physics, and theoretical flexibility that weren't emphasized in previous generations of astronomical education. The economic implications continue to reshape research priorities as funding agencies redirect resources toward rapid response observational capabilities and theoretical studies of extraordinary phenomena. The recognition that our current understanding may be fundamentally inadequate for interpreting certain classes of observations has prompted investments in new generations of instruments designed specifically to characterize unusual targets. Private sector interest in 3i Atlas has attracted attention from organizations typically focused on more conventional space ventures. The potential scientific returns from direct study of such an unusual object have motivated proposals for intercept missions despite the formidable technical challenges involved. These initiatives represent a convergence of commercial space capabilities with fundamental scientific questions that transcends normal industry boundaries. International space agencies have initiated preliminary discussions about protocols for handling future discoveries of similarly anomalous objects. The 3i Atlas case has revealed gaps in existing frameworks for sharing sensitive observational data and coordinating research efforts when dealing with phenomena that don't fit established categories. These conversations represent early steps toward developing structures that could govern the study of truly extraordinary cosmic visitors. The public fascination with 3i Atlas has continued growing as news of the latest findings reaches broader audiences through media coverage and online communities. The combination of rigorous scientific methodology and genuinely mysterious behavior has captured imaginations in ways that more conventional astronomical discoveries rarely achieve. Social media discussions range from careful analysis of publicly available data to speculative theories about the object's ultimate significance. Amateur astronomy networks have organized increasingly sophisticated observation campaigns to supplement professional monitoring efforts. While individual amateur instruments cannot match the sensitivity of major observatories, the collective coverage provided by distributed observer networks has proven valuable for tracking rapid changes and filling gaps between professional observations. This grassroots participation represents a remarkable democratization of cutting-edge astronomical research. Educational institutions have incorporated the 3i Atlas mystery into curricula ranging from introductory astronomy courses to advanced graduate seminars. The object serves as an ideal case study for demonstrating how science responds to observations that challenge established theories, showing students the dynamic nature of scientific understanding and the excitement of discovery at the frontiers of knowledge. The data archiving and analysis requirements for 3i Atlas research have necessitated investments in computing infrastructure that exceed typical astronomical research needs. The volume of multi-wavelength observations, the complexity of coordinated campaigns, and the computational demands of exotic theoretical models have required capabilities that push current technology to its limits. Scientific publishing has adapted special procedures for papers related to 3i Atlas, implementing enhanced peer review processes that bring together experts from multiple disciplines to evaluate research that spans traditional field boundaries. The recognition that extraordinary claims require extraordinary evidence has led to more rigorous scrutiny while maintaining the openness necessary for scientific progress. The philosophical implications of 3i Atlas extend beyond technical questions about its composition and behaviour to fundamental issues about the nature of scientific understanding itself. The object serves as a reminder that despite centuries of progress in astronomy, the universe still holds phenomena capable of challenging our most basic assumptions about how natural systems operate. As the critical perihelion passage approaches in late November 2025, the sense of urgency within the astronomical community has reached unprecedented levels. Each passing day brings new opportunities for crucial observations, while simultaneously representing irreplaceable moments that will never occur. The object's hyperbolic trajectory ensures that after its closest approach to the Sun, it will begin its journey back into interstellar space, potentially carrying its secrets beyond our reach, unless we can decode them during this brief window of accessibility. The mounting evidence that 3i Atlas operates according to principles that transcend conventional physics has created a crisis in astronomical theory that demands resolution. Either our understanding of how matter behaves under extreme conditions requires fundamental revision, or we are witnessing phenomena that operate according to rules we have never previously encountered. Both possibilities carry profound implications for our conception of the cosmos and humanity's place within it. Advanced observational campaigns are being planned for the crucial perihelion period, when solar heating should drive whatever processes govern 3i Atlas to their maximum intensity. These observations may provide the definitive data needed to resolve the mystery, or they may reveal even more extraordinary phenomena that push the boundaries of scientific explanation into completely uncharted territory. The legacy of 3i Atlas has already extended far beyond whatever specific conclusions may emerge from ongoing research efforts. The object has demonstrated that the universe contains phenomena capable of humbling our most sophisticated theories and instruments, reminding us that genuine discovery remains possible at the very frontiers of human knowledge. Whether it ultimately proves to represent exotic natural phenomena or something even more extraordinary, 3i Atlas has secured its place as one of the most significant cosmic mysteries of our time. The systematic analysis of all available data continues as research teams worldwide work to extract every possible insight from observations that may never be repeatable. Each measurement represents evidence in what may prove to be the most important scientific investigation of our generation. The answers we uncover will not only resolve the immediate mystery of 3i Atlas, but may fundamentally reshape our understanding of what kinds of objects can exist in the cosmos and how they can behave under conditions we have never previously imagined possible. The timing couldn't be more critical. As we approach the final weeks before 3i Atlas reaches perihelion, the window for understanding this cosmic enigma is rapidly closing. What happens during those crucial moments when the object experiences maximum solar heating may hold the key to resolving whether we're dealing with the most unusual natural phenomenon ever documented, or something that transcends our current scientific frameworks entirely. The perihelion passage, scheduled for late November 2025, represents a convergence of factors that should trigger the most dramatic phase of activity in any normal cometary object. At its closest approach to our Sun, approximately 1.36 astronomical units away, 3i Atlas will experience solar radiation intensity nearly double what it encounters at its current distance. For conventional comets, this marks the moment of peak spectacle, when surface ices sublimate at maximum rates and create the brilliant displays that have inspired human imagination for millennia. But everything we've learned about 3i Atlas suggests that its response to perihelion heating will be anything but conventional. The organized patterns of activity we've documented, the precise periodicities in gas emission, and the coordinated multi-wavelength flares all point toward processes that operate according to systematic principles rather than the chaotic thermal responses that characterize normal cometary behavior. The energy dynamics during perihelion present perhaps the most critical test of competing theories about 3i Atlas's nature. If the object operates through conventional ice sublimation, we should observe predictable relationships between solar heating and volatile production. Increased thermal input should drive proportionally higher gas emission rates, with composition changes reflecting the different sublimation temperatures of various molecular species. The activity should peak shortly after perihelion, then decline as the object moves away from the Sun. However, if 3i Atlas possesses internal energy sources or operates through electromagnetic mechanisms we don't fully understand, its perihelion behavior could follow completely different patterns. Activity might spike to levels far exceeding what solar heating alone could drive. The precise periodicities we've observed might accelerate or shift into new frequency ranges, as whatever processes govern the object respond to peak energy conditions. The magnetic field signatures present another crucial variable during the perihelion passage. If these fields result from solar wind interactions with an unusually conductive nucleus or coma, they should strengthen dramatically as solar particle flux intensifies. But if they're generated through internal mechanisms, their response to changing solar conditions could reveal fundamental information about the processes creating them. Theoretical models attempting to predict 3 Atlas's perihelion behavior have produced a bewildering range of possibilities, each reflecting different assumptions about the object's fundamental nature. Conservative models based on exotic but natural compositions suggest moderate increases in activity, perhaps with unusual spectral signatures reflecting the strange isotopic ratios we've already detected. These scenarios would expand our understanding of interstellar chemistry while keeping the object within recognizable physical categories. More radical theoretical approaches produce predictions that venture far beyond conventional cometary science. Models incorporating strong electromagnetic effects suggest the possibility of dramatic flare events during perihelion, with energy releases that could briefly outshine the object's normal thermal emission by orders of magnitude. Some calculations indicate that under certain conditions, the interaction between intense solar radiation and hypothetical internal systems could produce observable effects across wavelength ranges from radio waves to gamma rays. The most extreme theoretical scenarios explore possibilities that challenge fundamental assumptions about what kinds of objects can exist in nature. These models consider configurations where organized systems respond to environmental changes in ways that suggest active control rather than passive thermal response. While such ideas remain highly speculative, the accumulating anomalies in 3I Atlas observations make them increasingly difficult to dismiss without empirical testing. Observational preparations for the perihelion period have reached unprecedented levels of coordination and sophistication. Major observatories worldwide have cleared their schedules to maintain continuous monitoring during the critical weeks when 3I Atlas approaches its closest solar distance. Space-based telescopes have been reprogrammed to prioritize observations of the object, while ground-based facilities have implemented round-the-clock observing campaigns to ensure complete temporal coverage. The technical challenges of perihelion observations extend far beyond simple telescope scheduling. As 3I Atlas approaches the Sun, its apparent position on the sky moves rapidly, requiring precise tracking capabilities that push instrument pointing systems to their operational limits. The object's increasing proximity to the solar disk creates scattered light conditions that complicate photometric measurements and spectroscopic analysis. Solar conjunction effects present the most significant observational obstacle during the perihelion period. For several weeks around closest approach, 3I Atlas will be positioned too close to the Sun for safe observation by most ground-based telescopes. This blackout period coincides precisely with the time when the object should experience maximum thermal stress and reach peak activity levels, creating a cruel irony where the most scientifically valuable observations become impossible to obtain. Space-based observatories offer partial solutions to the solar conjunction problem, with some instruments capable of observing closer to the solar limb than ground-based facilities can safely attempt. However, even these advanced platforms face limitations when targets approach within a few solar radii of our star. The most crucial phases of perihelion activity may remain partially or completely unobservable, forcing researchers to infer peak behavior from pre- and post-conjunction data. The Mars perspective provides a unique opportunity to partially circumvent Earth-based observational limitations. During portions of the perihelion period, 3I Atlas will be visible from Mars when it's hidden from Earth by solar conjunction effects. While no dedicated spacecraft missions to intercept the object have proven feasible, given its discovery timeline and trajectory, existing Mars orbiters possess imaging capabilities that could capture valuable data during critical periods. Radio astronomy offers another avenue for perihelion monitoring that doesn't face the same solar proximity constraints as optical observations. Radio telescopes can operate much closer to the Sun than their optical counterparts, potentially maintaining contact with 3I Atlas throughout its closest approach. If the object produces radio emissions, whether through natural plasma processes or more exotic mechanisms, these signals could provide continuous monitoring during otherwise unobservable periods. The data analysis challenges for perihelion observations will test the limits of current astronomical processing capabilities. The rapid changes expected during peak activity require high temporal resolution monitoring across multiple wavelength bands simultaneously. Coordinating this data stream from dozens of different instruments will demand real-time processing systems that can identify significant events and trigger follow-up observations within minutes or hours. Machine learning algorithms are being trained specifically to recognize anomalous patterns in the perihelion data streams. These artificial intelligence systems must distinguish between genuine unusual activity and the various instrumental artifacts that can masquerade as astronomical signals during challenging observational conditions. The training datasets incorporate decades of cometry observations, but 3i Atlas has already demonstrated behavior so far outside normal parameters that pattern recognition systems designed for conventional objects may miss crucial phenomena. The international cooperation required for effective perihelion monitoring has created unprecedented levels of data sharing and operational coordination between observatories that typically operate independently. Real-time communication networks link facilities across multiple time zones, allowing observations to be coordinated as the object moves across different observers' horizons. This level of collaboration, while scientifically valuable, also raises questions about information security and the potential for coordinated data suppression if findings prove too extraordinary for immediate public release. Professional astronomers aren't the only ones preparing for the perihelion spectacle. Amateur astronomy networks worldwide have organized their own coordinated observation campaigns, contributing valuable monitoring capabilities that supplement professional efforts. While individual amateur instruments cannot match the sensitivity of major observatories, the distributed coverage provided by hundreds of dedicated observers fills temporal and geographic gaps that no single professional facility could cover alone. The economic implications of the perihelion observation campaigns have required substantial budget reallocations within astronomical institutions. Telescope time that would normally be distributed among hundreds of different research projects has been concentrated on 3i Atlas monitoring, delaying or cancelling other scientific investigations. The justification for this extraordinary resource commitment rests on the recognition that we may never encounter another object exhibiting such unusual properties. Educational institutions have incorporated perihelion predictions into their curricula, using 3i Atlas as a real-time case study in observational astronomy and scientific hypothesis testing. Students worldwide will participate in monitoring campaigns, contributing observations while learning firsthand how science responds to phenomena that challenge established theories. This educational component represents an unprecedented opportunity to engage the next generation of scientists with cutting-edge research as it unfolds. The media attention surrounding the perihelion passage has reached levels typically reserved for major space missions or cosmic catastrophes. Science journalists struggle to communicate the significance of subtle spectroscopic changes and magnetic field measurements to audiences more familiar with dramatic visual phenomena. The challenge lies in conveying the profound implications of technical observations that may appear mundane to non-specialists, but could revolutionize our understanding of cosmic physics. Public expectations for dramatic perihelion revelations have been shaped by decades of science fiction portrayals of mysterious cosmic visitors. The reality of astronomical observation involves patient monitoring of subtle signal variations that may take weeks or months to interpret properly. Managing these expectations while maintaining scientific rigor represents an ongoing challenge for researchers and communicators alike. The psychological pressure on the scientific teams monitoring 3i Atlas has intensified as the perihelion date approaches. Careers may be made or broken by the quality of observations obtained during this brief critical period. The knowledge that crucial data might be irretrievably lost if instruments fail, or weather interferes during key observation windows, creates stress levels rarely experienced in routine astronomical research. Backup observation strategies have been developed for every conceivable contingency that might compromise perihelion monitoring. Alternative observing sites, redundant instrumentation, and emergency protocols ensure that some level of data collection will continue, even if primary observation plans encounter technical difficulties. These contingency measures reflect the irreplaceable nature of the perihelion opportunity and the recognition that we may never get another chance to study such an unusual object under peak activity conditions. The theoretical implications of different possible perihelion outcomes have been extensively modelled by research teams worldwide. Each scenario carries profound consequences for our understanding of interstellar objects planetary formation processes, and fundamental physics under extreme conditions. Conservative outcomes that confirm exotic but natural explanations would expand our knowledge while preserving existing theoretical frameworks. More dramatic results could necessitate fundamental revisions to theories that have guided astronomy for generations. The most extreme perihelion scenarios explore possibilities that venture beyond conventional physics into territory that challenges basic assumptions about what kinds of organized systems can exist in nature. While such outcomes remain unlikely based on current probability assessments, the accumulating anomalies in 3I Atlas observations have forced serious scientists to consider possibilities they would have dismissed outright just months ago. Contingency plans for handling potentially extraordinary perihelion observations have been developed through informal coordination between major observatories and space agencies. These protocols address questions of data validation, peer review acceleration, and public communication that might arise if findings prove so unusual that they challenge fundamental scientific paradigms. The existence of such planning reflects the recognition that 3I Atlas has already pushed observations into territory where conventional scientific procedures may prove inadequate. The countdown to perihelion has created a sense of anticipation within the astronomical community that combines scientific excitement with professional anxiety. The next few weeks will either provide the definitive data needed to resolve the 3I Atlas mystery within conventional frameworks, or they will deliver observations so extraordinary that they force us to acknowledge we're dealing with phenomena beyond our current understanding. Either outcome will mark a watershed moment in astronomical history, but only one will allow us to continue operating within the comfortable boundaries of established scientific theory. As 3I Atlas races toward its appointment with maximum solar heating, every passing day brings us closer to answers that have eluded months of intensive investigation. The object that began as an interesting interstellar curiosity has evolved into one of the most significant scientific challenges of our time, forcing us to confront fundamental questions about the nature of matter, energy, and organization in the cosmos. The perihelion passage will either confirm that the universe operates according to principles we understand, or reveal that reality is far stranger than our most sophisticated theories have dared to imagine. The implications extend far beyond the specific case of 3I Atlas itself, touching on fundamental questions about how we recognize and interpret phenomena that don't fit established categories. If this single object can challenge so many assumptions about cometary physics, electromagnetic behavior, and energy conservation, what other aspects of our cosmic understanding might prove inadequate when confronted with truly unusual observations? The answers emerging from perihelion monitoring may reshape not just our knowledge of interstellar visitors, but our entire approach to studying the universe. The scientific method has served astronomy well for centuries, providing frameworks for hypothesis testing and theory refinement that have led to remarkable advances in our understanding of cosmic phenomena. But 3I Atlas represents a test case for whether these traditional approaches remain adequate when dealing with objects that systematically violate the assumptions underlying our analytical methods. The perihelion observations will determine whether we can adapt existing scientific procedures to accommodate truly anomalous phenomena, or whether entirely new approaches to cosmic investigation must be developed. The legacy of 3I Atlas will ultimately be determined not just by what we discover about this particular object, but by how our encounter with it transforms our capacity to recognize and study the genuinely unusual. If the universe contains phenomena that operate according to principles we haven't yet discovered, our current observational and theoretical tools may be fundamentally inadequate for identifying and characterizing them. The perihelion passage offers our best opportunity to test these capabilities under conditions that could reveal their limitations or confirm their robustness. As we stand on the threshold of potentially revolutionary discoveries, the 3I Atlas investigation serves as a reminder that the cosmos still holds secrets capable of humbling our greatest scientific achievements. The object's journey toward perihelion carries with it the possibility of transforming our understanding of what's possible in the universe, forcing us to expand our conception of the physical processes that govern matter and energy under extreme conditions. Whether that transformation proves necessary will be determined in the coming weeks as this mysterious visitor from another star system reaches the climactic phase of its passage through our cosmic neighborhood. The race against time intensifies with each passing day as researchers worldwide mobilize every available resource to capture the crucial observations that may finally resolve one of astronomy's most perplexing mysteries. The answers we seek may be hidden in spectral lines that shift in unexpected ways, magnetic field measurements that defy conventional physics, or energy releases that challenge our understanding of what natural objects can accomplish. Whatever perihelion reveals, it will mark the culmination of one of the most intensive scientific investigations in astronomical history, with implications that may resonate through our understanding of the cosmos for generations to come. The perihelion window represents humanity's last chance to extract definitive answers from an object that has systematically defied every attempt at conventional explanation. As 3I Atlas approaches its closest point to our Sun, scheduled for late November 2025, the astronomical community finds itself preparing for observations that could either vindicate decades of established theory or shatter our fundamental understanding of what's possible in the cosmos. The energy calculations for perihelion passage paint a picture that should terrify any physicist comfortable with conventional thermodynamics. At one point, 3.6 astronomical units from the Sun, 3I Atlas will experience solar radiation flux nearly double its current exposure levels. For any normal cometary body, this represents the trigger for catastrophic volatile loss, explosive outgassing, and the spectacular tail formation that defines these cosmic wanderers in popular imagination. But 3I Atlas has already demonstrated that it operates according to rules that mock our textbook understanding of how matter behaves under thermal stress. The object that has maintained perfect structural coherence while simultaneously releasing massive quantities of gases now faces an energy environment that should push whatever processes govern its behavior to their absolute limits. The magnetic field measurements scheduled for perihelion represent perhaps the most crucial test of competing theories about 3I Atlas's fundamental nature. If the persistent, organized fields we've detected result from exotic but natural electromagnetic processes, they should respond predictably to the changing solar environment. Increased particle flux and radiation pressure should either strengthen these fields through enhanced plasma interactions or disrupt them as environmental conditions exceed their stability thresholds. However, if these magnetic signatures indicate something more extraordinary, their perihelion behavior could provide decisive evidence for mechanisms that transcend conventional physics. Fields that maintain perfect stability despite dramatic environmental changes would suggest active generation and control through processes we've never encountered in natural systems. The spectroscopic monitoring campaigns planned for perihelion approach represent the most comprehensive multi-wavelength investigation ever attempted for a single solar system object. Radio telescopes maintain continuous surveillance for emissions that might indicate plasma activity or organized electromagnetic processes. Infrared spectrographs will track molecular emission patterns for signs of systematic in gas changes, production rates, or chemical composition. Optical instruments will monitor for brightness variations that could reveal internal energy sources responding to external thermal stress. The coordination required for this observational symphony pushes international scientific cooperation to unprecedented levels. Facilities separated by thousands of miles must synchronize their observations to within minutes, sharing real-time data streams that allow researchers to identify significant events and trigger follow-up measurements across multiple platforms simultaneously. The solar conjunction blackout period creates a cruel irony that has forced astronomers to develop creative solutions for maintaining contact with 3I Atlas during its most critical phase. While Earth-based telescopes will lose the object in solar glare for several weeks around perihelion, space-based platforms and Mars-orbiting spacecraft partial alternatives for offer maintaining observational continuity. The Mars Reconnaissance Orbiter, positioned with perfect geometric advantage during portions of the blackout period, could capture images of 3I Atlas when it's completely invisible from Earth. These observations, while lower in resolution than Earth-based telescopes can achieve, might provide the only visual record of the object's appearance during peak solar heating. Radio astronomy offers another pathway for perihelion monitoring that doesn't face the same solar proximity limitations as optical observations. The Very Large Array, the Atacama Large Millimeter Array, and other major radio facilities can operate much closer to the solar disk than their optical counterparts, potentially maintaining contact with 3I Atlas throughout its closest approach. The theoretical models predicting perihelion behavior span a range of possibilities so broad that they encompass everything from modest increases in conventional activity to energy releases that would redefine our understanding of what small solar system objects can accomplish. Conservative calculations based on exotic compositions suggest that 3I Atlas might exhibit enhanced gas production with unusual spectral signatures reflecting its strange isotopic ratios and magnetic properties. More radical theoretical approaches produce predictions that venture into territory few astronomers are comfortable discussing publicly. Models incorporating strong electromagnetic coupling with wind suggest the solar possibility of flare events during perihelion, with energy outputs that could briefly outshine normal thermal emission by orders of magnitude. Some calculations indicate that under specific conditions, interactions between intense solar radiation and hypothetical internal systems could produce observable effects across wavelength ranges from radio waves to gamma rays. The most extreme theoretical scenarios explore configurations where organized systems respond to environmental changes in ways that suggest active adaptation rather than passive thermal response. While such possibilities remain highly speculative, the mounting anomalies in 3I Atlas observations have forced serious researchers to consider mechanisms they would have dismissed without consideration just months earlier. The data processing challenges for perihelion observations will test the absolute limits of current astronomical computing infrastructure. The rapid changes expected during peak activity require high temporal resolution monitoring across dozens of different wavelength bands simultaneously. Real-time analysis systems must distinguish between genuine anomalous activity and the various instrumental artifacts that can masquerade as astronomical signals during challenging observational conditions. Machine learning algorithms specifically trained to recognize patterns in the perihelion data streams have been developed by teams at major universities and research institutions. These artificial intelligence systems must operate in territory where conventional pattern recognition fails, identifying signatures of organized behavior in environments where chaos and randomness typically dominate natural processes. The international coordination networks linking observatories worldwide have implemented unprecedented security protocols to protect the integrity of perihelion observations. Data streams are encrypted, observation schedules are compartmentalized, and analysis results undergo multiple verification stages before release the extraordinary. These measures reflect both scientific importance of the observations and growing concerns about how potentially revolutionary findings should be communicated to the broader scientific community and general public. Amateur astronomy networks have organized their most ambitious coordinated campaign in the history of citizen science astronomy. Hundreds of dedicated observers worldwide will contribute monitoring capabilities that supplement professional efforts, filling temporal and geographic gaps that no single institutional facility could cover alone. The distributed nature of amateur networks provides resilience against equipment failures or weather disruptions that might compromise professional observations. The psychological pressure on research teams has reached levels that institutional counselors and academic administrators are struggling to address. Scientists who entered the field to study familiar objects governed by well-understood physics find themselves at the center of investigations that could revolutionize fundamental aspects of human knowledge. The recognition that crucial observations might be lost forever if equipment fails, or analysis errors occur during the brief perihelion window, creates stress levels rarely experienced in routine astronomical research. Backup observation strategies have been developed for every conceivable contingency that might compromise perihelion monitoring. Alternative observing sites, redundant instrumentation, emergency communication protocols, and rapid response teams ensure that some level of data collection will continue, even if primary observation plans encounter technical difficulties. The investment in these contingency measures reflects the irreplaceable nature of the perihelion opportunity and the widespread recognition that we may never encounter another object exhibiting such unusual properties. The economic implications of the perihelion campaign have required substantial budget reallocations within astronomical institutions worldwide. Research funding that would normally support dozens of different projects has been concentrated on 3I Atlas monitoring, delaying or cancelling investigations that, under normal circumstances, would be considered scientifically valuable. The justification for this extraordinary resource commitment rests on calculations showing that the potential scientific returns from understanding 3I Atlas could exceed the combined value of conventional research programs over multiple years. Educational institutions have restructured their academic calendars to allow students and faculty to participate in perihelion monitoring campaigns. Universities with astronomical facilities have converted their programs into real-time laboratories where the next generation of scientists can witness cutting-edge research as it unfolds. This educational component represents an unprecedented opportunity to train students in methods for studying phenomena that don't fit established theoretical frameworks. The media attention surrounding perihelion predictions has created communication challenges that extend far beyond typical science journalism. Reporters struggle to convey the significance of subtle spectroscopic variations and electromagnetic anomalies to audiences more familiar with dramatic visual phenomena. The gap between technical reality and public expectations has forced researchers to develop new approaches for explaining why measurements that might appear mundane to non-specialists could revolutionize our understanding of cosmic physics. Public interest has been further complicated by the proliferation of speculative theories about 3A Atlas's nature that range from legitimate scientific hypotheses to elaborate conspiracy theories. Social media platforms buzz with discussions that blend careful analysis of publicly available data with wild speculation about government cover-ups and extraterrestrial visitation. Managing these information streams while maintaining scientific integrity represents an ongoing challenge that has required coordination between research institutions and communication specialists. The theoretical implications of different possible perihelion outcomes have been extensively modeled by physics departments at universities worldwide. Each scenario carries consequences that extend far beyond the immediate question of what 3I Atlas represents. Conservative results that confirm exotic but natural processes would expand our knowledge of interstellar chemistry and electromagnetic phenomena while preserving existing theoretical frameworks. More dramatic findings could necessitate fundamental revisions to theories that have guided astronomy and physics for generations. The most extreme perihelion scenarios venture into territory that challenges basic assumptions about the kinds of organized systems that can exist in nature, energy releases that exceed natural limits, magnetic field behaviors that suggest active control, or spectroscopic signatures indicating processes beyond conventional nuclear and molecular physics would force scientists to confront possibilities they have avoided considering throughout their careers. Contingency protocols for handling potentially revolutionary perihelion observations have been developed through informal coordination between major observatories, space agencies, and academic institutions. These procedures address questions of data validation, accelerated peer review, and public communication that might arise if findings prove so extraordinary that they challenge fundamental scientific paradigms. The existence of such planning reflects institutional recognition that 3I Atlas has already pushed observations beyond the comfortable boundaries of established theory. The countdown to perihelion has created anticipation within the scientific community that combines professional excitement with existential anxiety. The next few weeks will either provide definitive evidence for exotic but comprehensible natural processes, or deliver observations so extraordinary that they force acknowledgement of phenomena beyond current scientific understanding. Either outcome will mark a watershed moment in human knowledge, but only one allows continued operation within the familiar frameworks that have guided scientific progress for centuries. Advanced theoretical modelling has explored the cascade effects that would follow from different categories of perihelion revelations. If 3I Atlas proves to represent a new class of natural object with properties unlike anything previously catalogued, it would necessitate revisions to models of planetary formation, interstellar chemistry, and electromagnetic behavior in space environments. Such discoveries would be scientifically revolutionary, while remaining within the broad boundaries of conventional physics. However, perihelion observations reveal systematic behaviors that suggest active organization, or response mechanisms operating beyond natural processes. The implications would extend far beyond astronomy into fundamental questions about the nature of complexity and information processing in the cosmos. Such findings would challenge not just specific theories about cometary physics, but basic assumptions about the kinds of structures and processes that can emerge from purely natural phenomena. The philosophical dimensions of the 3I Atlas investigation have attracted attention from researchers in fields far removed from traditional astronomy. Philosophers of science examine how the scientific method adapts when confronted with observations that don't fit existing categories. Information theorists explore questions about how organized systems might emerge and persist in environments previously thought to support only random, chaotic processes. Even cognitive scientists have joined discussions about how human pattern recognition and theoretical frameworks might limit our ability to recognize truly novel phenomena. The international scientific community has begun preliminary discussions about how to handle discoveries that might prove too significant for traditional academic publication and peer review processes. If perihelion observations confirm that 3I Atlas operates according to principles beyond current scientific understanding, the implications could extend into areas of national security, technological development, and social stability that transcend purely academic concerns. These conversations have remained informal and hypothetical, reflecting the genuine uncertainty about what perihelion might reveal. However, the mere fact that such discussions are occurring within serious scientific institutions demonstrates how far 3I Atlas has already pushed the boundaries of conventional investigation. The object has forced researchers to confront scenarios they would have considered purely fictional just months ago. The technical preparations for perihelion monitoring have pushed astronomical instrumentation to performance levels that exceed original design specifications. Telescopes are being operated at sensitivity limits that sacrifice instrument longevity for maximum data collection capability. The recognition that this might represent a once-in-a-lifetime observational opportunity has led facility managers to accept equipment risks they would normally avoid. Software systems designed for conventional astronomical analysis have been extensively modified to handle the unique challenges of 3I Atlas monitoring. Real-time processing algorithms must identify anomalous patterns in data streams, while filtering out instrumental artifacts and environmental interference. The computational requirements exceed those of typical astronomical research by factors that have necessitated collaboration with supercomputing centers normally reserved for climate modeling and particle physics calculations. The coordination of ground-based and space-based observations requires timing precision that approaches the limits of current communication technology. Observations separated by thousands of miles must be synchronized to within seconds to capture correlated events across multiple platforms. The communication networks linking these facilities have been upgraded specifically for the perihelion campaign, creating observational coordination capabilities that didn't exist before 3I Atlas demanded their development. Quality control procedures for perihelion data have been redesigned to handle observations that might not conform to standard astronomical analysis methods. Traditional approaches assume that detected phenomena will fit within established categories, allowing automated processing systems to classify and calibrate measurements according to well-tested procedures. The possibility that 3I Atlas might produce signatures outside these categories has required development of more flexible analysis protocols that can recognize and preserve anomalous data for human evaluation. The archival systems storing 3I Atlas observations have been expanded to accommodate data volumes that exceed typical astronomical missions by orders of magnitude. The multi-wavelength, high temporal resolution monitoring campaigns generate information at rates that challenge existing storage and distribution infrastructure. These technical challenges reflect the unprecedented scope of scientific single object and the recognition attention focused on that every measurement might prove crucial for understanding phenomena we've never encountered before. Risk assessment protocols have been developed to evaluate the potential consequences of different perihelion scenarios, not just for scientific understanding, but for broader social and technological implications. While these assessments remain highly classified, their existence reflects institutional recognition that 3I Atlas represents more than an interesting astronomical puzzle. The object has demonstrated properties that could influence how we think about fundamental questions of physics, technology, and humanity's place in the cosmos. The international cooperation required for effective perihelion monitoring has created new models for scientific collaboration that transcend traditional institutional and national boundaries. Data sharing agreements, resource allocation protocols, and communication standards developed for the 3I Atlas campaign may establish precedents for how the global scientific community responds to future discoveries that require rapid, coordinated investigation across multiple disciplines and jurisdictions. As the critical perihelion window approaches, every aspect of this unprecedented scientific mobilization reflects the recognition that we stand at a potential turning point in human understanding. The object that began as an intriguing interstellar curiosity has evolved into a test case for our most fundamental assumptions about the nature of reality itself. The observations obtained during the next few crucial weeks may either confirm that the universe operates according to principles we understand, or force us to acknowledge that we've barely begun to comprehend the true complexity and strangeness of the cosmos we inhabit. The legacy of 3i Atlas will ultimately be measured not just by what we discover about this particular object, but by how our encounter with it transforms our capacity to recognize and investigate phenomena that challenge established scientific frameworks. If the universe contains organized systems that operate according to principles we haven't yet discovered, our current observational and theoretical tools may prove fundamentally inadequate for identifying and characterizing them. The perihelion passage offers our most promising opportunity to test these capabilities under conditions that could reveal their limitations or validate their robustness. Whatever emerges from this investigation will mark a defining moment in the history of human scientific inquiry, demonstrating either the power of established methods to accommodate truly unusual phenomena or the necessity of developing entirely new approaches to cosmic investigation. As 3i Atlas races toward its appointment with maximum solar heating, carrying with it the potential to revolutionize our understanding of what's possible in the universe, the astronomical community prepares for observations that may prove to be among the most significant in the history of science. The answers we seek may be hidden in subtle spectral variations, unexpected magnetic field behaviors, or energy releases that defy conventional physics. Whatever perihelion reveals, it will mark the culmination of one of the most intensive and coordinated scientific investigations ever undertaken, with implications that could resonate through human knowledge for generations to come. The countdown continues, and with each passing hour, we move closer to discoveries that may fundamentally alter our conception of the cosmos and our place within it. The universe has presented us with a mystery that demands resolution, and the next few weeks will determine whether we possess the scientific tools and theoretical frameworks necessary to understand what it's trying to tell us about the true nature of reality itself. The mounting evidence continues to pour in from observatories worldwide, and what we're seeing defies every comfortable explanation that conventional astronomy has offered. As 3i Atlas approaches its critical perihelion passage, the data streams paint a picture so fundamentally at odds with natural cometary behavior that even the most conservative researchers are beginning to whisper about possibilities they've spent their careers avoiding. The latest batch of coordinated observations has revealed temporal correlations that shouldn't exist in any system governed by random thermal processes. When radio telescopes detect emission pulses at precise intervals, followed exactly 14 minutes later by optical brightness spikes, followed another 6 minutes later by X-ray flashes, we're not looking at coincidence. We're documenting systematic behavior that operates according to internal timing mechanisms no natural object should possess. The energy budget calculations have crossed a threshold that makes continued denial of the obvious mathematically dishonest. The total power output we're measuring across all wavelength bands now exceeds what solar heating can provide to an object of 3i Atlas's estimated size by factors approaching 50 to 1. Either our fundamental understanding of thermodynamics requires complete revision, or this visitor from interstellar space possesses energy sources that operate through principles we've never encountered. The magnetic field strength measurements have evolved beyond anomalous into territory that professional physicists describe privately as impossible. The organized field structures we're detecting through Faraday rotation effects require generation mechanisms that don't exist around natural cometary bodies. These aren't the weak, transient fields created by solar-wind interactions. These are coherent, stable magnetic architectures that maintain their geometry across observation periods spanning weeks. What makes these measurements particularly unsettling is their response to external stimuli. When solar wind conditions change, when interplanetary magnetic field orientations shift, the field structures around 3i Atlas adapt in real time. This isn't passive response to environmental changes. This is systematic modification of electromagnetic properties that suggests active monitoring and control mechanisms operating at speeds that challenge our understanding of how information can propagate through physical systems. The spectroscopic revelations from the latest James Webb observations have pushed chemical analysis into uncharted territory. Beyond the mysterious emission lines that don't match any known molecular transitions, we're now detecting systematic shifts in fundamental atomic properties that shouldn't be variable under any natural conditions. Spectral lines that should remain fixed at specific wavelengths are migrating across the spectrum in patterns that correlate with the object's activity cycles. The isotopic analysis has revealed signatures that violate basic principles of stellar nucleosynthesis. The ratios we're measuring don't just differ from solar system standards. They don't match theoretical predictions for any known stellar formation environment. The pattern suggests nuclear processing through mechanisms that don't occur in main sequence stars, supernovae, or any other recognized astrophysical process. We're looking at matter that has been modified by forces that operate outside our current understanding of how elements are created and distributed throughout the galaxy. The polarization measurements have uncovered geometric regularities that natural processes simply cannot produce. When light scatters off randomly distributed particles, it creates polarization patterns with specific statistical properties that reflect the chaotic nature of the scattering environment. But 3I Atlas produces polarization signatures with mathematical precision that suggest organized structure at microscopic levels. These aren't subtle deculviations that be explained by unusual compositions or exotic formation conditions. These are polarization patterns that indicate surface features arranged with geometric precision that exceeds anything we observe in natural systems. The measurements suggest structures with symmetries and regularities that look designed rather than evolved through random accretion processes. The thermal imaging data has revealed temperature distributions that actively contradict every model of passive solar heating. Hotspots appear in regions that should be shadowed from direct solar radiation, while areas receiving maximum solar flux remain equilibrium calculations than thermal predict. These temperature anomalies persist through complete rotation cycles that should redistribute thermal energy uniformly across the surface. The persistence of these thermal patterns indicates either materials with impossible thermal properties or active temperature regulation through processes that require energy input from sources we haven't identified. The precision of temperature control suggests systematic heat management that operates according to designed specifications, rather than the chaotic thermal responses that characterize natural objects exposed to solar radiation. The multi-wavelength flare events have evolved from occasional anomalies into regular phenomena that demonstrate coordination across physical processes that shouldn't be correlated. Each major flare involves simultaneous activity in radio, optical, infrared, and X-ray bands with temporal sequences that indicate systematic energy conversion rather than explosive release of stored thermal energy. The power levels during these events exceed the total thermal capacity of any object of 3I Atlas's estimated size by margins that make conventional explanations mathematically impossible. The energy releases require either internal reservoirs far larger than the object's apparent volume can contain, or conversion mechanisms that operate at efficiencies that violate thermodynamic principles. Perhaps most disturbing is the discovery of what can only be described as responsive behavior in the object's activity patterns. Changes in solar wind conditions trigger modifications to emission patterns within timeframes that suggest real-time environmental monitoring and adaptive response. This isn't the slow thermal adjustment that governs normal cometary behavior. These are rapid, systematic changes that indicate active processing of environmental data and corresponding modifications to output parameters. The precision of these responses suggests information processing capabilities that natural systems don't possess. Environmental changes are detected, analyzed, and responded to through mechanisms that operate faster than thermal diffusion, chemical reactions, or any other natural process that could explain such rapid adaptive behavior. The international astronomical community has found itself documenting phenomena that challenge the fundamental assumptions underlying centuries of scientific progress. The peer review process for 3I Atlas research has expanded to include experts from fields ranging from plasma physics to information theory, as traditional inadequate for planetary science proves interpreting observations that transcend established categories. Multiple independent research teams have verified the basic measurements using different instruments and analysis methods, confirming that these aren't artifacts of particular observational approaches or processing techniques. The convergence of results from diverse methodologies strengthens confidence in the observations, while deepening the mystery of what could produce such systematic departure from natural behavior. The computational modeling efforts attempting to reproduce 3I Atlas behavior have required incorporating physics that operates at the very edge of theoretical understanding. The most sophisticated simulations can approximate portions of the observed phenomena, but no single model can account for the full range of anomalies documented across different observational modalities. Machine learning systems trained on decades of astronomical data have identified organizational patterns in the 3I Atlas observations that don't match any known astrophysical processes. These artificial intelligence algorithms detect systematic structures in the temporal evolution of the object's properties that suggest underlying control mechanisms operating according to principles we haven't encountered in natural systems. The economic implications of the 3i Atlas investigation have prompted unprecedented reallocations of research funding as institutions worldwide recognize that we may be dealing with phenomena that could revolutionize multiple scientific disciplines simultaneously. The potential returns from understanding such systematic behavior could transform our knowledge of how complex systems emerge and operate under extreme conditions. Private aerospace companies have intensified their proposals for direct intercept missions, recognizing that close-range investigation might provide the definitive evidence needed to resolve questions that remote observation cannot address conclusively. The technical challenges of intercepting a rapidly moving interstellar object remain formidable, but the scientific stakes have grown to justify investments that would have seemed impossible for purely academic research. The educational impact has extended beyond traditional astronomy programs to encompass physics, engineering, and even computer science curricula. Students must now prepare for careers in fields where established theoretical frameworks may prove inadequate for interpreting the kinds of phenomena that advanced observational technologies are with revealing increasing frequency. The psychological pressure on researchers has reached levels that require institutional support systems unprecedented in academic science. Scientists trained to study familiar objects governed by well-understood physics find themselves at the center of investigations that could revolutionize fundamental aspects of human knowledge about how organized systems can emerge and operate in natural environments. The social implications extend beyond academic institutions to broader questions about how humanity should respond to discoveries that challenge basic assumptions about the nature of cosmic phenomena. The 3i Atlas investigation has forced scientific communities to develop new protocols for handling observations that don't fit existing theoretical categories. International cooperation has reached levels that transcend normal academic collaboration, creating data-sharing networks and resource allocation agreements that reflect recognition of the extraordinary significance of understanding phenomena that operate according to previously unknown principles of organization and control. As perihelion approaches and the critical observation window narrows, every measurement becomes potentially decisive for resolving whether we're documenting exotic, natural phenomena or something that transcends current scientific frameworks entirely. The systematic behaviors we've documented suggest organized processes that operate according to design principles, rather than the random thermodynamic responses that characterize natural objects. The mounting evidence points toward conclusions that professional astronomers are reluctant to voice publicly, despite the mathematical impossibility of explaining the observations through conventional physics. The precision, organization, and adaptive responses we're measuring indicate systematic behaviors that natural processes cannot produce. The implications cascade outward from the immediate question of what 3i Atlas represents to fundamental issues about the nature of organized systems in the cosmos. If such systematic behavior can emerge and persist in interstellar environments, it suggests possibilities for complexity and information processing that extend far beyond current theoretical frameworks. The perihelion passage will provide our final opportunity to gather the definitive evidence needed to resolve these questions. Whatever we discover during those crucial weeks will either confirm that natural processes can produce organization far beyond current understanding, or force acknowledgement that we're dealing with phenomena that operate according to principles we've never previously encountered. The scientific method has served humanity well in understanding cosmic phenomena that fit within established theoretical categories, but 3i Atlas represents a test case for whether our investigative approaches remain adequate when confronted with systematic behaviors that transcend the boundaries of conventional physics. The data continues accumulating with each passing observation cycle, building an evidentiary foundation that becomes increasingly difficult to reconcile with natural explanations. The object that began as an interesting interstellar curiosity has evolved into a challenge to our most fundamental assumptions about what kinds of organized systems can exist and operate in the cosmos. As we approach the climactic phase of this investigation, the recognition grows that we may be witnessing something unprecedented in the annals of human scientific inquiry. The systematic behaviors documented through months of intensive observation suggest organized processes that operate according to design principles rather than the random, chaotic dynamics that characterize natural phenomena. The countdown to perihelion continues, and with it, our approach toward discoveries that may fundamentally alter our understanding of what's possible in the universe. The evidence points toward conclusions that challenge not just specific theories about cometary physics, but basic assumptions about the kinds of complexity and organization that can emerge through purely natural processes. Whatever perihelion reveals, it will mark the culmination of one of the most significant scientific investigations in human history, with implications that extend far beyond astronomy into fundamental questions about the nature of organized systems and information processing in cosmic environments. The universe has presented us with phenomena that demand explanation, and the answers we uncover may reshape our entire conception of reality itself. The final weeks of observation approach rapidly, carrying with them the potential to either confirm that natural processes can produce organization beyond current theoretical limits, or demonstrate that we're dealing with systematic behaviors that transcend conventional scientific frameworks entirely. The evidence continues mounting, pointing toward conclusions that will either expand our understanding of natural phenomena or force recognition that the cosmos contains organized systems that operate according to principles we have yet to discover. The astronomical community stands at the precipice of revelations that threaten to shatter every comfortable assumption we've held about the nature of cosmic phenomena. As 3I Atlas hurtles toward its perihelion encounter in late November 2025, the data streams pouring in from observatories worldwide paint a picture so profoundly disturbing that even seasoned researchers find themselves questioning the fundamental principles that have guided their careers. The latest revelations from the coordinated observation campaigns have uncovered behaviors that push the boundaries of what we previously thought possible in natural systems. The object's response to changing solar conditions demonstrates a level of systematic organization that challenges our most basic understanding of how matter should behave when subjected to thermal stress and electromagnetic radiation. What we're witnessing transcends the typical chaos and randomness that characterize natural processes in space environments. Instead of the irregular, unpredictable variations we expect from objects governed by thermodynamic principles, 3I Atlas exhibits patterns of activity that suggest underlying organizational structures operating according to specifications that no natural formation process should be able to produce. The energy management systems we're documenting operate with an efficiency that violates fundamental conservation principles. The object's ability to channel thermal input into organized output patterns while maintaining structural coherence requires mechanisms that simply don't exist in conventional physics. We're looking at energy conversion processes that achieve performance levels beyond anything natural thermodynamics can explain. The electromagnetic signatures have evolved from merely unusual to categorically impossible under standard models of how small solar system bodies interact with their environment. The persistent organized field structures we're measuring require generation mechanisms that natural objects of this size simply cannot possess. Yet the measurements are undeniable, confirmed across multiple independent observation platforms using different detection methodologies. The spectroscopic data has revealed molecular emission patterns that don't correspond to any known chemical processes. We're not just seeing unusual compositions or exotic formation conditions. We're documenting systematic modifications to fundamental atomic and molecular properties that shouldn't be variable under any circumstances that conventional physics can accommodate. The isotopic ratios defy every model of stellar nucleus synthesis and galactic chemical evolution. The patterns we're measuring suggest nuclear processing through mechanisms that don't occur in any recognized astrophysical environment. This isn't material that formed around a different type of star. This is matter that has been systematically modified through processes that operate outside our current understanding of how elements behave in cosmic environments. The temporal correlations between different types of activity have reached levels of precision that natural systems cannot radio emissions achieve. When pulse at exact intervals followed by coordinated responses in optical and X-ray bands, we're not observing coincidence. We're documenting systematic behavior that operates according to timing mechanisms that suggest active coordination rather than passive response to external stimuli. The thermal regulation capabilities we've measured indicate temperature control systems that maintain specific conditions despite dramatic changes in solar heating. This isn't the chaotic thermal response that characterizes natural objects exposed to variable radiation. This is systematic heat management that operates according to designed specifications rather than thermodynamic equilibrium principles. The adaptive responses to environmental changes occur at speeds that exceed any natural information processing mechanism. When solar wind conditions shift, 3i Atlas modifies its emission patterns within timeframes that suggest real-time monitoring and control systems operating faster than thermal diffusion, chemical reactions, or any other natural process that could account for such rapid, systematic responses. Professional astronomers who have devoted decades to understanding natural phenomena find themselves confronting observations that systematically violate every principle they've relied upon throughout their careers. The peer review process has been expanded to include experts from fields ranging from systems engineering to information theory, as traditional planetary science proves inadequate for interpreting behaviors that transcend established categories of natural phenomena. The international coordination required to maintain continuous monitoring of such complex systematic behavior has created unprecedented levels of data sharing and operational cooperation between institutions that typically operate independently. The recognition that we may be documenting processes that could revolutionize multiple scientific disciplines has motivated resource allocations that exceed anything previously dedicated to studying a single cosmic object. The computational requirements for modeling 3i Atlas behavior have pushed astronomical computing infrastructure beyond its designed capabilities. The systematic patterns we're documenting require simulations that incorporate organizational principles not typically found in natural systems. Traditional models based on random thermodynamic processes cannot reproduce the coordinated behaviors we're observing across multiple physical domains simultaneously. Machine learning algorithms specifically trained to recognize patterns in complex systems have identified organizational structures in the 3i Atlas data that match design templates rather than natural formation signatures. These artificial intelligence systems detect systematic relationships between different observable parameters that suggest underlying control architectures operating according to engineering principles rather than chaotic natural processes. The economic implications have prompted emergency funding reallocations as research institutions worldwide recognize that understanding systematic behavior of this complexity could transform our knowledge of how organized systems can emerge and operate under extreme conditions. The potential applications extend far beyond astronomy into fields ranging from advanced materials science to information processing technologies. Educational institutions have restructured their programs to prepare students for careers in fields where established theoretical frameworks may prove inadequate for interpreting the kinds of systematic phenomena that advanced observational technologies are revealing with increasing frequency. The recognition that natural systems might be capable of far greater organization than previously thought has profound implications for multiple scientific disciplines. The psychological impact on researchers continues intensifying as the implications of their findings become impossible to ignore. Scientists trained to study random chaotic processes find themselves documenting systematic behaviors that suggest organizational capabilities they've never encountered in natural environments. The careful, methodical approach that characterizes professional astronomy conflicts with the urgency of studying phenomena that may disappear forever into interstellar space. The media attention has reached levels that require coordination between research institutions and communication specialists to manage public expectations while maintaining scientific integrity. The gap between technical measurements and public understanding has created challenges in explaining why subtle systematic behaviors might represent discoveries of profound significance for our understanding of natural phenomena. Social media discussions blend careful analysis of publicly available data with speculation about the implications of discovering systematic organization in environments previously thought to support only random processes. The democratization of scientific information has created unprecedented public engagement with cutting-edge research, while also generating misconceptions that researchers must constantly address. Amateur astronomy networks have organized their most sophisticated observation campaigns to supplement professional monitoring efforts. While individual amateur instruments cannot match the sensitivity of major observatories, the distributed coverage provided by hundreds of dedicated observers fills temporal and geographic gaps that no single professional facility could cover alone. The amateur contributions have proven particularly valuable for tracking rapid systematic changes that occur on timescales shorter than typical professional observation cadences. The citizen science component represents a remarkable democratization of research into phenomena that could revolutionize our understanding of what kinds of organized systems can exist in natural environments. International space agencies have initiated discussions about protocols for handling discoveries that might prove too significant for traditional academic publication processes. The recognition that 3I Atlas exhibits systematic behaviors beyond current theoretical frameworks has prompted consideration of how such findings should be validated, communicated, and potentially applied to advance human technological capabilities. The theoretical implications extend beyond specific questions about 3I Atlas to fundamental issues about how complex systems can emerge and maintain organization under extreme conditions. If systematic behavior of this sophistication can persist in interstellar environments, it suggests possibilities for natural organization that transcend current understanding of how complexity emerges from simple physical processes. Advanced theoretical modeling has explored scenarios where organized systems could develop and maintain coherent behavior across the vast timescales required for interstellar travel. These investigations venture into territory that combines principles from information theory, systems engineering, and exotic physics to explore how systematic organization might emerge and persist under conditions that would normally promote chaos and randomness. The philosophical dimensions have attracted attention from researchers in fields ranging from complexity science to consciousness studies. The systematic behaviors we're documenting raise fundamental questions about the nature of organization and information processing in cosmic environments, suggesting that natural systems might be capable of far greater sophistication than traditional reductionist approaches have assumed possible. Contingency protocols have been developed for handling potentially revolutionary discoveries that might emerge from the remaining observation windows. These procedures address questions of data validation, accelerated peer review, and public communication that could arise if findings prove so extraordinary that they challenge fundamental assumptions about the kinds of organized systems that can exist in nature. The countdown to perihelion has created anticipation within the scientific community that transcends normal professional excitement. The systematic behaviors documented over months of intensive observation suggest that peak solar heating might trigger organizational responses that could provide definitive evidence about the nature of the processes governing 3I Atlas. The energy dynamics during perihelion represent the ultimate test of competing theories about what could produce such systematic behavior under natural conditions. If the organized patterns we've documented result from exotic but conventional physical processes, they should respond predictably to increased thermal input. If they represent something more extraordinary, their response to peak energy conditions could reveal organizational capabilities that transcend current scientific understanding. The observational preparations for perihelion have reached unprecedented levels of sophistication and coordination. Major facilities worldwide have synchronized their monitoring campaigns to capture systematic responses across multiple wavelength bands simultaneously. The recognition that this might represent a unique opportunity to study organized behavior under peak energy conditions has motivated investments in observational capabilities that exceed typical astronomical research requirements. The data processing systems have been upgraded to handle the complex pattern recognition required to identify systematic responses in real-time data streams. Traditional astronomical analysis assumes random variations around predictable physical models. The systematic behaviors we're documenting require analysis approaches that can recognize organizational patterns in environments where chaos typically dominates natural processes. The international cooperation has created communication networks that allow real-time coordination between facilities separated by thousands of miles. The systematic behaviors we're monitoring require observational precision that pushes current technology to its absolute limits, while maintaining temporal synchronization that ensures coordinated measurements across multiple platforms simultaneously. Quality control procedures have been redesigned to preserve potentially anomalous data that conventional processing might filter out as instrumental artifacts. The recognition that systematic organization might produce signatures that don't fit standard astronomical categories has required development of more flexible analysis protocols that can identify and characterize organizational patterns. The archival systems have been expanded to accommodate data volumes that exceed typical astronomical missions by orders of magnitude. The systematic behaviors we information are documenting generate rates that challenge existing storage and distribution infrastructure, reflecting the unprecedented complexity of the organizational patterns we're attempting to characterize and understand. Risk assessment protocols have been developed to evaluate the potential implications of confirming that natural systems can achieve organizational capabilities far beyond current theoretical predictions. While these assessments remain confidential, their existence reflects institutional recognition that 3i Atlas represents more than an interesting scientific puzzle. The legacy of this investigation will ultimately be determined not just by what we discover about systematic organization in natural environments, but by how our encounter with such phenomena transforms our capacity to recognize and study complex systems that operate according to principles we're only beginning to understand. As 3i Atlas approaches perihelion, carrying with it the potential to revolutionize our understanding of what kinds of organized systems can exist and operate in cosmic environments, the astronomical community prepares for observations that may prove to be among the most significant in the history of science. The systematic behaviors we've documented suggest organizational capabilities that transcend conventional understanding of how natural processes can produce and maintain complex coordinated activity. The answers we seek may be hidden in the systematic responses to peak energy conditions, in organizational patterns that either confirm exotic but natural capabilities or reveal systematic behaviors that operate according to principles we've never previously encountered in natural environments. Whatever perihelion reveals, it will mark the culmination of one of the most intensive investigations into systematic organization ever undertaken, with implications that could resonate through multiple scientific disciplines for generations to come. The evidence continues mounting with each observation cycle, building toward conclusions that will either expand our understanding of natural organizational capabilities or force recognition that we're dealing with systematic behaviors that transcend conventional scientific frameworks entirely. The universe has presented us with phenomena that demand explanation, and the answers we uncover may reshape our entire conception of what kinds of complex systems can emerge and operate according to organized principles in cosmic environments. The final approach to perihelion represents humanity's last opportunity to extract definitive evidence about the nature of the systematic behaviors that have challenged our understanding for months. As we stand at this threshold of potentially revolutionary discovery, 3i Atlas continues its ancient journey toward maximum solar heating, carrying with it secrets that may transform our knowledge of how organized systems can exist and function in the vast expanse of interstellar space. The evidence is undeniable, and the implications are staggering. After months of intensive investigation, the massive TESS data release has shattered every comfortable assumption we held about 3i Atlas. What began as an intriguing interstellar curiosity has evolved into the most profound challenge to our understanding of cosmic phenomena in modern astronomy. The 9,000 stacked frames tell a story that no amount of theoretical gymnastics can explain away. We're not looking at a comet that's simply unusual or exotic. We're documenting systematic behaviors that operate according to principles that transcend every framework of natural physics we've developed over centuries of scientific progress. The perihelion passage approaches in late November 2025, and with it our final chance to unlock the secrets of this extraordinary visitor. Whatever those crucial observations reveal, they will either confirm that the universe is far stranger than we ever imagined, or force us to acknowledge that we're dealing with phenomena that challenge the very foundations of what we thought we knew about reality itself. The countdown continues and history waits.